Chapter 1. A Tutorial Introduction. Let us begin with a quick introduction in C. Our aim is to show the essential elements of the language in real programs, but without getting bogged down in details, rules, and exceptions. At this point, we are not trying to be complete or even precise, save that the examples are meant to be correct. We want to get you as quickly as possible to the point where you can write useful programs, and to do that we have to concentrate on the basics. Variables and constants, arithmetic, control flow, functions, and the rudiments of input and output. We are intentionally leaving out of this chapter features of C that are important for writing bigger programs. These include pointers, structures, most of C's rich set of operators, several control flow statements, and the standard library. This approach and its drawbacks. Most notable is that the complete story on any particular feature is not found here, and the tutorial, by being brief, may also be misleading. And because the examples do not use the full power of C, they are not as concise and elegant as they might be. We have tried to minimize these effects, but be warned. Another drawback is that later chapters will necessarily repeat some of this chapter. We hope that the repetition will help you more than it annoys. In any case, experienced programmers should be able to extrapolate from the material in this chapter to their own programming needs. Beginners should supplement it by writing small, similar programs of their own. Both groups can use it as a framework on which to hang the more detailed descriptions that begin in Chapter 2. 1.1 Getting started. The only way to learn a new programming language is by writing programs in it. The first program to write is the same for all languages. Print the words hello, world. This is a big hurdle. To leap over it, you have to be able to create the program text somewhere, compile it successfully, load it, run it, and find out where your output went. With these mechanical details mastered, everything else is comparatively easy. In C, the program to print hello, world, is #include stdio hmain, a printf hello, world \n. Just how to run this program depends on the system you are using. As a specific example, on the Unix operating system, you must create the program in a file whose name ends in .c, such as hello.c, then compile it with the command cc hello.c. If you haven't botched anything, such as omitting a character or misspelling something, the compilation will proceed silently and make an executable file called a.out. If you run a.out by typing the command a.out, it will print hello, world. On other systems, the rules will be different. Check with a local expert. Now, for some explanations about the program itself. A C program, whatever its size, consists of functions and variables. A function contains statements that specify the computing operations to be done, and variables store values used during the computation. C functions are like the subroutines and functions in Fortran or the procedures and functions of Pascal. Our example is a function named main. Normally, you are at liberty to give functions whatever names you like, but main is special. Your program begins executing at the beginning of main. This means that every program must have a main somewhere. Main will usually call other functions to help perform its job, some that you wrote, and others from libraries that are provided for you. The first line of the program, #include stdio.h, tells the compiler to include information about the standard input-output library. The line appears at the beginning of many C source files. The standard library is described in Chapter 7 and Appendix B. One method of communicating data between functions is for the calling function to provide a list of values, called arguments, to the function it calls. The parentheses after the function name surround the argument list. In this example, main is defined to be
the parentheses after the function name surround the argument list.
The parentheses after the function name surround the argument list. In this example, main is defined to be a function that expects no arguments, which is indicated by the empty list. Include information about standard #include stdio. Library define a function called main that received no argument values. Statements of main are enclosed in braces. Main calls library function printf hello, world \n. To print this sequence of characters \n represents the new line character, The first C program, the statements of a function are enclosed in braces. The function contains only one main statement. Printf, hello, world \n. A function is called by naming it, followed by a parenthesized list of arguments, so this calls the function printf with the argument, hello, world \n. Printf is a library function that prints output, in this case the string of characters between the quotes. A sequence of characters in double quotes, like hello, world \n, is called a character string or a string constant. For the moment, our only use of character strings will be as arguments for printf and other functions. The sequence \n in a string is C notation for the new line character, which when printed advances the output to the left margin on the next line. If you leave out the \n, a worthwhile experiment, you will find that there is no line advance after the output is printed. You must use \n to include a new line character in the printf argument if you try something like printf, hello, world. The C compiler will produce an error message. Printf never supplies a new line character automatically, so several calls may be used to build up an output line in stages. Our first program could just as well have been written #include stio, -h, main, a printf, hello, printf, world, printf, \n, to produce identical output. Notice that represents only a single character. An escape sequence, like, provides a \n general and extensible mechanism for representing hard-to-type or invisible characters. Among the others that C provides are \t for tab, \b for backspace, / for the double quote, and / for the / itself. There is a complete list in section 2.3. Exercise 1-1. Run the hello, world program on your system. Experiment with leaving out parts of the program to see what error messages you get. Exercise 1-2. Experiment to find out what happens when \c, where C is some character not listed above. Prince's argument string contains 1.2 variables and arithmetic expressions. The next program uses the formula OC sadface 5/9 of 32 to print the following table of Fahrenheit temperatures and their centigrade or Celsius equivalents. 1 - 17 20 - 6 44 60 15 80 26 137 120 48 140 60 160 70 1 180 82 293 trillion 220 billion 104 million 240,000 115 260 trillion 120 6 billion 280 million 137,300 148. The program itself still consists of the definition of a single function named main. It is longer than the one that printed hello, world, but not complicated. It introduces several new ideas, including comments, declarations, variables, arithmetic expressions, loops, and formatted output. Hashtag includes stio, h, / print Fahrenheit Celsius table. For FAHR equals 0, 20. 300/main, in FAHR, Celsius, in lower, upper, step, lower equals 0, / lower limit of temperature scale / upper equals 300, / upper limit / step equals 20, / step size */ FAHR equals lower, while FAHR equals upper, a Celsius equals 5 *, FAHR 32/9, printf, %d \t %d \n, FAHR, Celsius, FAHR equals FAHR plus step. The two lines. / print Fahrenheit Celsius table for FAHR equals 0, 20, 300 * are a comment, which in this case explains briefly what the program does. Any characters between / and * are ignored by the compiler. They may be used freely to make a program easier to understand. Comments may appear anywhere where a blank, tab, or new line can. In C, all variables must be declared before they are used, usually at the beginning of the function before any executable statements. A declaration announces the properties of variables, It consists of a name and a list of variables, such as int FHR Celsius, int lower, upper, step. The type int means that the variables listed are integers. By contrast with which means float, floating point, i.e., numbers that may have a fractional part. The range of both int and float depends on the machine you are using. 16 bits ints, which lie between minus 32,768 and plus 32,767, are common, as are 32-bit ints. A float number is typically a 32-bit quantity, with at least 6 significant digits and magnitude generally between about 10 to 38 and 1038. C provides several other data types besides and including int float, char character, a single byte short integer long integer double precision floating point. The size of these objects is also machine dependent. There are also arrays, structures, and unions of these basic types, pointers to them, and functions that return them, all of which we will meet in due course. Computation in the temperature conversion program begins with the assignment statements lower equals 0, upper equals 300, step equals 20, which set the variables to their initial values. Individual statements are terminated by semicolons. Each line of the table is computed the same way, so we use a loop that repeats once per output line. This is the purpose of the while loop. While FAHR equals upper. The while loop operates as follows. The condition in parentheses is tested. If it is true, FAHR is less than or equal to upper. The body of the loop, the 3 statements enclosed in braces, is executed. Then the condition is retested, and if true, the body is executed again. When the test becomes false, FAHR exceeds upper, the loop ends, and execution continues at the statement that follows the loop. There are no further statements in this program, so it terminates. The body of a while can be one or more statements enclosed in braces, as in the temperature converter, or a single statement without braces, as in while I less than j, I equals 2 asterisk I. In either case, we will always indent the statements controlled by the while by one tab stop, which we have shown as 4 spaces, so you can see at a glance which statements are inside the loop. The indentation emphasizes the logical structure of the program. Although C compilers do not care about how a program looks, proper indentation and spacing are critical in making programs easy for people to read. We recommend writing only one statement per line and using blanks around operators to clarify grouping. The position of braces is less important, although people hold passionate beliefs. We have chosen one of several popular styles. Pick a style that suits you, then use it consistently. Most of the work gets done in the body of the loop. The Celsius temperature is computed and assigned to the variable Celsius by the statement Celsius equals 5 asterisk FAHR 32/9. The reason for multiplying by 5 and dividing by 9 instead of just multiplying by 5/9 is that in C, as in many other languages, integer division truncates. Any fractional part is discarded, since 5 and 9 are integers. May 9th would be truncated to 0, and so all the Celsius temperatures would be reported as 0. This example also shows a bit more of how works. Is a general-purpose printf output formatting function, which we'll describe in detail in Chapter 7. Its first argument is a string of characters to be printed, with each % indicating where one of the other, second, third arguments is to be substituted and in what form it is to be printed. For instance, %d specifies an integer argument, so the statement printf %d \t %d \n FAHR Celsius causes the values of the two integers FAHR and Celsius to be printed, with a tab \t between them. Each % construction in the first argument of is paired with the corresponding second printf argument, third argument, etc. They must match up properly by number and type, or you will get wrong answers. By the way, printf is not part of the C language. There is no input or output defined in C itself. Printf is just a useful function from the standard library of functions that are normally accessible to C programs. The behavior of printf is defined in the ANSI standard, however, so its properties should be the same with any compiler and library that conforms to the standard. In order to concentrate on C itself, we don't talk much about input and output until Chapter 7. In particular, we will defer formatted input until then. If you have to input numbers, read the discussion of the function scanf in section 7.4. Scanf is like printf, except that it reads input instead of writing output. There are a couple of problems with the temperature conversion program. The simpler one is that the output isn't very pretty because the numbers are not right justified. That's easy to fix. If we augment each %d in the printf statement with a width, the numbers printed will be right justified in their fields. For instance, we might say printf %3d %6d \n FAHR Celsius to print the first number of each line in a field 3 digits wide and the second in a field 6 digits wide, like this: 0 -17 20 -6 44 60 15 80 20 6 137. The more serious problem is that because we have used integer arithmetic, the Celsius temperatures are not very accurate. For instance, 0 of is actually about -17.80 C, not -17. To get more accurate answers, we should use floating point arithmetic instead of integer. This requires some changes in the program. Here is the second version. #include /diode h / print Fahrenheit Celsius table for FAHR equals 0, 20, 300, floating point version * main. Float FAHR Celsius. Float lower, upper, step. Lower equals 0. / lower limit of temperature scale / upper equals 300 / upper limit / step equals 20 / step size * FAHR equals lower. While FAHR equals upper, a Celsius equals 5.0 / 9.0 * FAHR 32.0. Printf %3.0 f %6.1 f \n FAHR Celsius. FAHR equals FAHR plus step. This is much the same as before, except that and are declared to be and FAHR Celsius float. The formula for conversion is written in a more natural way. We were unable to use 5/9 in the previous version because integer division would truncate it to 0. A decimal point in a constant indicates that it is floating point, however, so 5.0 / 9.0 is not truncated because it is the ratio of two floating point values. If an arithmetic operator has integer operands, an integer operation is performed. If an arithmetic operator has one floating point operand and one integer operand, however, the integer will be converted to floating point before the operation is done. If we had written FAHR 32, the 32 would be automatically converted to floating point. Nevertheless, writing floating point constants with explicit decimal points even when they have integral values emphasizes their floating point nature for human readers. The detailed rules for when integers are converted to floating point are in Chapter 2. For now, notice that the assignment FAHR equals lower and the test, while FAHR equals upper also work in the natural way. These converted to before the operation is done. Int float. The conversion specification says that a floating point number, here is to printf %3.0 f FAHR, be printed at least 3 characters wide, with no decimal point and no fraction digits. %6.1 f
%6.1 f describes another number, Celsius.
%6.1 f
%6.1 f describes another number.
%6.1 f
%6.1 f 0 -17.8
0 -17
0 -17.8 20 -6
0 -17
0 -17.8 20 -6.7 44.4. Width and precision may be omitted from a specification.
Width and precision may be omitted from a specification. %6f says that the number is to be at least 6 characters wide. %.2f specifies 2 characters after the decimal point, but the width is not constrained, and %f merely says to print the number as floating point. %d print as decimal integer. %6d print as decimal integer, at least 6 characters wide. %f print as floating point. %6f print as floating point, at least 6 characters wide. %.2f print as floating point, 2 characters after decimal point. %6.2f print as floating point, at least 6 wide and 2 after decimal point. Among others, printf also recognizes %o for octal, %x for hexadecimal, %c for character, %s for character string, and %% for itself. Exercise 1-3. Modify the temperature conversion program to print a heading above the table. Exercise 1-4. Write a program to print the corresponding Celsius to Fahrenheit table.
Modify the temperature conversion program to print a heading above the table. Exercise 1-4. Write a program to print the corresponding Celsius to Fahrenheit table. 1.3 The first statement. There are plenty of different ways to write a program for a particular task. Let's try a variation on the temperature converter. Hashtag includes dio, h, / print Fahrenheit Celsius table /main. In FHR, for FHR equals 0, FHR less than or equal to 300, FHR equals FHR plus 20, printf, %3d %6.1f \n, FHR, 5.0/9.0, FHR, 32. This produces the same answers, but it certainly looks different. One major change is the elimination of most of the variables. Only FHR remains, and we have made it an int. The lower and upper limits and the step size appear only as constants in the first statement, itself a new construction. And the expression that computes the Celsius temperature now appears as the third argument of printf instead of a separate assignment statement. This last change is an instance of a general rule. In any context where it is permissible to use the value of some type, you can use a more complicated expression of that type. Since the third argument of printf must be a floating point value to match the %6.1f, any floating point expression can occur here. The statement is a loop, a generalization of if you compare it to the earlier for while its operation should be clear. Within the parentheses, there are 3 parts, separated by semicolons. The first part, the initialization FHR equals 0, is done once, before the loop proper is entered. The second part is the test or condition that controls the loop. FHR less than or equal to 300. This condition is evaluated. If it is true, the body of the loop, here a single tint, is executed. Then the increment step, FHR equals FHR plus 20 is executed, and the condition reevaluated. The loop terminates if the condition has become false. As with the while, the body of the loop can be a single statement or a group of statements enclosed in braces. The initialization, condition, and increment can be any expressions. The choice between and is arbitrary, based on which seems clearer.
The is while for usually appropriate for loops in
The is while for usually appropriate for loops in which the initialization and increment are single statements and logically related. Since it is more compact than while and it keeps the loop control statements together in one place. Exercise 1-5. Modify the temperature conversion program to print the table in reverse order, that is, from 300 degrees to 0. 1.4 Symbolic constants. A final observation before we leave temperature conversion forever. It's bad practice to bury magic It's bad practice to bury magic numbers like 320 in a program. They convey little information to someone who might have to read the program later, and they are hard to change in a systematic way. One way to deal with magic numbers is to give them meaningful names. A number-defined line defines a symbolic name or symbolic constant to be a particular string of characters, number-defined name replacement list. Thereafter, any occurrence of name, not in quotes and not part of another name, will be replaced by the corresponding replacement text. The name has the same form as a variable name, a sequence of letters and digits that begins with a letter. The replacement text can be any sequence of characters, it is not limited to numbers. Number include ANSI and GT number define lower 0 / lower Number include ANSI and GT number define lower 0 / lower limit of table / number define upper 300 / upper limit / number define step 20 / step size / print Fahrenheit Celsius table * main, int Fahrenheit. 4. Fahrenheit equals lower, Fahrenheit and LT equals upper, Fahrenheit equals Fahrenheit plus step, print F. %3D %6.1 F \n, Fahrenheit, 5.0 / 9.0, *, Fahrenheit 32. The quantities lower, upper and step are symbolic constants, not variables, so they do not appear in declarations. Symbolic constant names are conventionally written in uppercase so they can be readily distinguished from lowercase variable names. Notice that there is no semicolon at the end of a number-defined line. 1.5 Character input and output. We are going to consider a family of related programs for processing character data. You will find that many programs are just expanded versions of the prototypes that we discuss here. The model of input and output supported by the standard library is very simple.
The model of input and output supported by the standard library is very simple. Text input or output, regardless of where it originates or where it goes to, is dealt with as streams of characters. A text stream is a sequence of characters divided into lines. Each line consists of 0 or more characters followed by a new line character. It is the responsibility of the library to make each input or output stream confirm this model. The C programmer using the library need not worry about how lines are represented outside the program. The standard library provides several functions for reading or writing one character at a time, of which getChar and putChar are the simplest. Each time it is called, getChar reads the next input character from a text stream and returns that as its value. That is after C equals getChar, the variable C contains the next character of input. The characters normally come from the keyboard. Input from files is discussed in Chapter 7. The function putChar prints a character each time it is called. PutChar C prints the contents of the integer variable C as a character, usually on the screen. Calls to putChar and printf may be interleaved. The output will appear in the order in which the calls are made. 1.5.1 File copying. Given, and you can write a surprising amount of useful code without getChar putChar, knowing anything more about input and output. The simplest example is a program that copies its input to its output one character at a time. Read a character while character is not end-of-file indicator. Output the character, just read. Read a character converting this into C gives. Hashtag includes diode, */ copy input to output. First version * main. Int C equals getChar, while C equals yof, putChar C equals getChar. The relational operator, equals, means not equal to. What appears to be a character on the keyboard or screen is, of course, like everything else, stored internally just as a bit pattern. The type char is specifically meant for storing such character data, but any integer type can be used. We used int for a subtle but important reason. The problem is distinguishing the end of input from valid data. The solution is that getChar returns a distinctive value when there is no more input, a value that cannot be confused with any real character. This value is called EOF, for end of file. We must declare C to be a type big enough to hold any value that getChar returns. We can't use char since C must be big enough to hold EOF in addition to any possible char. Therefore, we use int. EOF is an integer defined in stio.h, but the specific numeric value doesn't matter as long as it is not the same as any char value. By using the symbolic constant, we are assured that nothing in the program depends on the specific numeric value. The program for copying would be written more concisely by experienced C programmers. In C, any assignment such as C equals getChar is an expression and has a value, which is the value of the left-hand side after the assignment. This means that assignment can appear as part of a larger expression. If the assignment of a character to C is put inside the test part of a while loop, the copy program can be written this way. Hashtag includes stio, h / copy input to output, second version * main, ANSI C. While C equals getChar equals EOF, put char C, the while gets a character, assigns it to C, and then tests whether the character was themed off file signal. If it was not, the body of the while is executed, printing the character. The while then repeats. When the end of the input is finally reached, the while terminates, and so does main. This version centralizes the input. There is now only one reference to getChar, and shrinks the program. The resulting program is more compact, and, once the idiom is mastered, easier to read. You'll see this style often. It's possible to get carried away and create impenetrable code, however, a tendency that we will try to curb. The parentheses around the assignment, within the condition, are necessary. The precedence of equals is higher than that of equals, which means that in the absence of parentheses, the relational test equals would be done before the assignment equals. So the statement C equals getChar equals EOF is equivalent to C equals getChar equals EOF. This has the undesired effect of setting C to 0 or 1, depending on whether or not the call of getChar returned end of file. More on this in Chapter 2. Exercise 1 to 6. Verify that the expression getChar equals EOF is 0 or 1. Exercise 1 to 7. Write a program to print the value of EOF. 1.5.2 Character counting. The next program counts characters. It is similar to the copy program. Hashtag includes stio, h / count characters and input, first version * main, along ANSI. ANSI equals 0, while getChar equals EOF. ++ ANSI, printf, %LD / n ANSI. The statement ++ ANSI presents a new operator, ++, which means increment by 1. You could instead write ANSI equals ANSI 1, but is more concise and often more efficient. There is a corresponding operator to +++ ANSI decrement by 1. The operators and can be either prefix operators or postfix ++. ANSI operators and C++. These two forms have different values and expressions, as will be shown in Chapter 2, but ++NC and NC++ both increment NC. For the moment, we will stick to the prefix form. The character counting program accumulates its count in a long variable instead of an int. Long integers are at least 32 bits. Although on some machines, int and long are the same size, on others an int is 16 bits, with a maximum value of 32,767, and it would take relatively little input to overflow an int counter. The conversion specification %LD tells printf that the corresponding argument is a long integer. It may be possible to cope with even bigger numbers by using a double precision. We will also use a statement instead of a to illustrate another way to write float. For while, the loop hashtag includes stio, h / count characters and input, second version * main, double NC. For NC equals 0, gecker equals EOF ++ NC, printf, %.0f \n and c. A printf uses %f for both float and double. %.0f suppresses the printing of the decimal point and the fraction part, which is 0. The body of this for loop is empty because all the work is done in the test and increment parts. But the grammatical rules of C require that a for statement have a body. The isolated semicolon, called a null statement, is there to satisfy that requirement. We put it on a separate line to make it visible. Before we leave the character counting program, observe that if the input contains no characters, the while or for test fails on the very first call to get char, and the program produces 0. The right answer. This is important. One of the nice things about while and for is that they test at the top of the loop before proceeding with the body. If there is nothing to do, nothing is done, even if that means never going through the loop body. Programs should act intelligently when given zero-length input. The while and for statements help ensure that programs do reasonable things with boundary conditions. 1.5.3 Line counting. The next program counts input lines. As we mentioned above, the standard library ensures that an input text stream appears as a sequence of lines, each terminated by a new line. Hence, counting lines is just counting new lines. Hashtag includes diode, h / count lines in input * main. Int c, nl. nl equals 0, while c equals getchar, equals eof, if c equals \n, plus nl, printf, %d \n nl. The body of the while now consists of an if, which in turn controls the increment the plus nl. If statement tests the parenthesized condition, and if the condition is true, executes the statement or group of statements in braces that follows. We have again indented to show what is controlled by what. The double equals sign equals is the C notation for is equal to, like Pascal's single equals or Fortran's EQ. This symbol is used to distinguish the equality test from the single equals that C uses for assignment. A word of caution: newcomers to C occasionally write equals when they mean equals. As we will see in Chapter 2, the result is usually a legal expression, so you will get no warning. A character written between single quotes represents an integer value equal to the numerical value of the character in the machine's character set. This is called a character constant, although it is just another way to write a small integer. So, for example, is a character constant. In the ASCII character set, its value is 65, the internal representation of the character. A, of course, is to be preferred over 65. Its meaning is obvious, and it is independent of a particular character set. The escape sequences used in string constants are also legal in character constants, so \n stands for the value of the new line character, which is 10 in ESCI. You should note carefully that \n is a single character, and in expressions is just an integer. On the other hand, \n is a string constant that happens to contain only one character. The topic of strings versus characters is discussed further in Chapter 2. Exercise 1-8. Write a program to count blanks, tabs, and new lines. Exercise 1-9. Write a program to copy its input to its output, replacing each string of one or more blanks by a single blank. Exercise 1-10. Write a program to copy its input to its output, replacing each tab by \t, each backspace by \b, and each backslash by \\. This makes tabs and backspaces visible in an unambiguous way. 1.5. Word counting. The fourth in our series of useful programs counts lines, words, and characters, with the loose definition that a word is any sequence of characters that does not contain a blank, tab, or new line. This is a barebones version of the Unix program WC. Hashtag includes diode, h, hashtag define in1 * inside a word / hashtag define out 0 / outside a word / count lines, words, and characters in input * main. Int c, nl, nw, nc, state equals out, nl equals nw equals nc equals 0, while c equals getchar equals eof. plus plus NC. If C equals backslash N plus plus NL. If C equals backslash N C equals backslash T. State equals out. Else if state equals out. A state equals IN plus plus NW. Printf %d backslash N NL NW NC. Every time the program encounters the first character of a word, it counts one more word. The variable state records whether the program is currently in a word or not. Initially, it is not in a word, which is assigned the value out. We prefer the symbolic constants in and out to the literal values 1 and 0 because they make the program more readable. In a program as tiny as this, it makes little difference, but in larger programs, the increase in clarity is well worth the modest extra effort to write it this way from the beginning. You'll also find that it's easier to make extensive changes in programs where magic numbers appear only as symbolic constants. The line NL equals NW equals NC equals 0 sets all three variables to 0. This is not a special case, but a consequence of the fact that an assignment is an expression with the value and assignments associated from right to left. It's as if we had written NL equals NW equals NC equals 0. The operator means or, so the line. If C equals backslash NC equals backslash T says if C is a blank or C is a new line or C is a tab. Recall that the escape sequence backslash T is a visible representation of the tab character. There is a corresponding operator and for and. Its precedence is just higher than. Expressions connected by and or are evaluated left to right, and it is guaranteed that evaluation will stop as soon as the truth or falsehood is known. If C is a blank, there is no need to test whether it is a new line or tab, so these tests are not made. This isn't particularly important here, but is significant in more complicated situations, as we will soon see. The example also shows an else, which specifies an alternative action if the condition part of an if statement is false. The general form is if expression statement 1 else. Statement 2 1 and only one of the two statements associated with an if-else is performed. If the expression is true, statement 1 is executed. If not, statement 2 is executed. Each statement can be a single statement or several embraces. In the word count program, the one after the else is an if that controls two statements in braces. Exercise 1 to 11. How would you test the word count program? What kinds of input are most likely to uncover bugs if there are any? Exercise 1 to 12. Write a program that prints its input one word per line. 1.6 arrays. Let us write a program to count the number of occurrences of each digit of white space characters, blank, tab, new line, and of all other characters. This is artificial, but it permits us to illustrate several aspects of C in one program. There are 12 categories of input, so it is convenient to use an array to hold the number of occurrences of each digit, rather than 10 individual variables. Here is one version of the program. Hashtag includes diode, h / count digits, white space, others * main, int C, I, white, another, int digit 10, white equals another equals 0, for I equals 0, I less than 10, plus I digit I equals 0. While C equals getchar equals yof if C equals 0 and C equals 9, plus digit C dash 0. Else if C equals backslash N C equals backslash T, plus and white, else plus another. Printf digits equals, for I equals 0, I less than 10, plus I, printf, %d, digit I, printf, white space equals %d, other equals %d backslash N, white another. The output of this program on itself is digits equals 930000001, white space equals 123, other equals 345. The declaration. Int digit 10 declares digit to be an array of 10 integers. Array subscripts always start at 0 in C, so the elements are digit 0, digit 1, digit 9. This is reflected in the for loops that initialize and print the array. A subscript can be any integer expression, which includes integer variables like I and integer constants. This particular program relies on the properties of the character representation of the digits. For example, the test. If C equals 0 and C equals 9, determines whether the character in C is a digit. If it is, the numeric value of that digit is C. 0. This works only if 0, 1, 9 have consecutive increasing values. Fortunately, this is true for all character sets. By definition, are just small integers, so variables and constants are identical to char in arithmetic expressions. This is natural and convenient. For example, is an integer ANSI C-0 expression with a value between 0 and 9 corresponding to the character 0 to 9 stored in C, and thus a valid subscript for the array in digit. The decision as to whether a character is a digit, white space, or something else is made with the sequence. If C equals 0 and C equals 9, plus digit C-0, else if C equals C equals backslash and C equals backslash T, plus and white. Else plus another. The pattern if, condition 1, statement 1, else if, condition 2, statement 2, else. Statement occurs frequently in programs as a way to express a multi-way decision. The conditions are evaluated in order from the top until some condition is satisfied. At that point, the corresponding statement part is executed, and the entire construction is finished. Any statement can be several statements enclosed in braces. If none of the conditions is satisfied, the statement after the final else is executed if it is present. If the final else and statement are omitted, as in the word count program, no action takes place. There can be any number of else-if condition statement groups between the initial if and the final else. As a matter of style, it is advisable to format this construction as we have shown. If each if were indented past the previous else, a long sequence of decisions would march off the right side of the page. The switch statement, to be discussed in Chapter 4, provides another way to write a multi-way branch that is particularly suitable when the condition is whether some integer or character expression matches one of a set of constants. For contrast, we will present a switch version of this program in Section 3.4. Exercise 1 to 13. Write a program to print a histogram of the lengths of words and its input. It is easy to draw the histogram with the bars horizontal. A vertical orientation is more challenging. Exercise 1 to 14. Write a program to print a histogram of the frequencies of different characters and its input. 1.7 functions. In C, a function is equivalent to a subroutine or function in Fortran, or a procedure or function in Pascal. A function provides a convenient way to encapsulate some computation, which can then be used without worrying about its implementation. With properly designed functions, it is possible to ignore how a job is done. Knowing what is done is sufficient. C makes the SU of functions easy, convenient, and efficient. You will often see a short function defined and called only once, just because it clarifies some piece of code. So far we have used only functions like and that have been printf, getchar, putchar provided for us. Now it's time to write a few of our own. Since C has no exponentiation operator, like the of Fortran, let us illustrate the mechanics of function definition by writing a function power, m, n, to raise an integer m to a positive integer power n. That is, the value of power, 2, 5, is 32. This function is not a practical exponentiation routine, since it handles only positive powers of small integers. But it's good enough for illustration. The standard library contains a function pow, x, y, that computes xy. Here is the function power and a main program to exercise it, so you can see the whole structure at once. Hashtag includes diode, h-bint power, int m int n, /* test power function */ main, in I for I equals 0, I less than 10, plus plus I, printf, %d backslash n, I, power, 2, I, power, dash 3, I, return 0. Slash asterisk power, raise base to nth power, n equals 0 asterisk slash int power, int base int n, I and I, p equals 1, for I equals 1, I equals n, plus plus I, p equals p asterisk base, return p. A function definition has this form. Return type function name, parameter declarations, if any. Declaration statements. Function definitions can appear in any order and in one source file or several, although no function can be split between files. If the source program appears in several files, you may have to say more to compile and load it than if it all appears in one, but that is an operating system matter, not a language attribute. For the moment, we will assume that both functions are in the same file, so whatever you have learned about running C programs will still work. The function is called twice by in the line power main. Printf, %d backslash n, I, power, 2, I, power, dash 3, I. Each call passes 2 arguments to power, which each time returns an integer to be formatted and printed. In an expression, power, 2, I, is an integer just as 2 and I are. Not all functions produce an integer value. We will take this up in Chapter 4. The first line of power itself. Impube, imbase, inena.
Declares the parameter types and names, and the type of the result that the function returns. The names used by power for its parameters are local to power, and are not visible to any other function. Other routines can use the same names without conflict. This is also true of the variables I and p. The I in power is unrelated to the I in main. We will generally use parameter for a variable named in the parenthesized list in a function. The terms formal argument and actual argument are sometimes used for the same distinction. The value that computes is returned to by the statement. Any expression power main return may follow return expression. A function need not return a value. A return statement with no expression causes control, but no useful value, to be returned to the caller, as does falling off the end of a function by reaching the terminating right brace. And the calling function can ignore a value returned by a function. You may have noticed that there is a statement at the end of since is a return main. Main function like any other, it may return a value to its caller, which is in effect the environment in which the program was executed. Typically, a return value of 0 implies normal termination. Non-zero values signal unusual or erroneous termination conditions. In the interests of simplicity, we have omitted return statements from our main functions up to this point, but we will include them hereafter. As a reminder that programs should return status to their environment.
As a reminder that programs should return status to their environment. The declaration. Int power, int base in n. Just before main says that power is a function that expects 2 arguments and returns an int. This declaration, which is called a function prototype, has to agree with the definition and uses of power. It is an error if the definition of a function or any uses of it do not agree with its prototype. Parameter names need not agree. Indeed, parameter names are optional in a function prototype, so for the prototype we could have written int power, int. Well-chosen names are good documentation, however, so we will often use them. A note of history. The biggest change between ANSI C and earlier versions is how functions are declared and defined. In the original definition of C, the power function would have been written like this. / power, raise base to nth power, n equals 0 / old style version, * power, base, n int base, n, I int I, p equals 1, for I equals 1, I equals n, plus I, p equals p * base, return p. The parameters are named between the parentheses, and their types are declared before opening the left brace. Undeclared parameters are taken as int. The body of the function is the same as before. The declaration of power at the beginning of the program would have looked like this. In power, no parameter list was permitted, so the compiler could not readily check that power was being called correctly. Indeed, since by default power would have been assumed to return an int, the entire declaration might well have been omitted. The new syntax of function prototypes makes it much easier for a compiler to detect errors in the number of arguments or their types. The old style of declaration and definition still works in ANSI C, at least for a transition period, but we strongly recommend that you use the new form when you have a compiler that supports it. Exercise 1.15. Rewrite the temperature conversion program of section 1.2 to use a function for conversion. 1.8 arguments call by value. One aspect of C functions may be unfamiliar to programmers who are used to some other languages, particularly Fortran. In C, all function arguments are passed by value. This means that the called function is given the values of its arguments in temporary variables rather than the originals. This leads to some different properties than are seen with call by reference, languages like Fortran or with var parameters in Pascal, in which the called routine has access to the original argument, not a local copy. Call by value is an asset, however, not a liability. It usually leads to more compact programs with fewer extraneous variables because parameters can be treated as conveniently initialized local variables in the called routine. For example, here is a version of power that makes use of this property. /*power, raise base to nth power, n equals 0, version 2 */int power, int base, int n int p. 4, p equals 1, n greater than 0. And p equals p * base, return p. The parameter n is used as a temporary variable and is counted down, a loop that runs for backwards, until it becomes 0. There is no longer a need for the variable I. Whatever is done to n inside power has no effect on the argument that power was originally called with. When necessary, it is possible to arrange for a function to modify a variable in a calling routine. The caller must provide the address of the variable to be set, technically a pointer to the variable, and the called function must declare the parameter to be a pointer and access the variable indirectly through it. We will cover pointers in Chapter 5. The story is different for arrays. When the name of an array is used as an argument, the value passed to the function is the location or address of the beginning of the array. There is no copying of array elements. By subscripting this value, the function can access and alter any argument of the array. This is the topic of the next section. 1.9 Character arrays. The most common type of array in C is the array of characters. To illustrate the use of character arrays and functions to manipulate them, let's write a program that reads a set of text lines and prints the longest. The outline is simple enough. While there's another line, if it's longer than the previous longest, save it. Save its length. Print longest line. This outline makes it clear that the program divides naturally into pieces. One piece gets a new line, another saves it, and the rest controls the process. Since things divide so nicely, it would be well to write them that way too. Accordingly, let us first write a separate function getLine to fetch the next line of input. We will try to make the function useful in other contexts. At the minimum, getLine has to return a signal about possible end of file. A more useful design would be to return the length of the line, or 0 if end of file is encountered. 0 is an acceptable end of file return because it is never a valid line length. Every text line has at least one character. Even a line containing only a new line has length 1. When we find a line that is longer than the previous longest line, it must be saved somewhere. This suggests a second function, copy, to copy the new line to a safe place. Finally, we need a main program to control, and here is the result. getLine copy. Hashtag includes diode, h, hashtag define maxline 1000 / maximum input line length / int getLine, char line, int maxline, void copy, char to, char from, / print the longest input line * main. int len, /* current line length / at max, slash maximum length seen so far slash char line, max line, slash current input line, slash char longest, max line, slash longest line saved here, asterisk slash. Max equals 0, while len equals get line, line max line, 0 if len max, a max equals len, copy, longest line. If max 0, forward slash asterisk there is a line asterisk slash printf, %s, longest, return 0. Slash asterisk get line, read a line into s, return length asterisk slash and get line, char s, int lim, ANSI I for I equals 0, I'm lim, 1 and C equals get char, equals EOF and ANSI, equals backslash n, plus I s, I equals C. If C equals backslash n, s, I equals C, plus I. Ses, I equals backslash 0, return I, a forward slash asterisk copy from into 2, assume 2 is big enough asterisk slash void copy, char 2, char from, and I equals 0, while 2I equals from I equals backslash 0, plus I. The functions getLine and copy are declared at the beginning of the program, which we assume is contained in one file, and communicate through a pair of arguments and a return value. In main getLine, the arguments are declared by the line. Int getLine, char s, int lim, which specifies that the first argument, s, is an array and the second is an integer. The lim, purpose of supplying the size of an array in a declaration is to set aside storage. The length of an array s is not necessary in getLine since its size is set in main. GetLine uses return to send a value back to the caller, just as the function power did. This line also declares that getLine returns an int. Since int is the default return type, it could be omitted. Some functions return a useful value. Others, like copy, are used only for their effect and return no value. The return type of is which states explicitly that no value is returned. Copy void puts the character, the null character, whose value is 0, at the end of the getLine, \0, array it is creating, to mark the end of the string of characters. This conversion is also used by the C language, when a string constant like hello \n appears in a C program. It is stored as an array of characters containing the characters in the string and terminated with a \0 to mark the end. The format specification expects the corresponding argument to be a string %s printf represented in this form. Copy also relies on the fact that its input argument is terminated with a \0 and copies this character into the output. It is worth mentioning in passing that even a program as small as this one presents some sticky design problems. For example, what should main do if it encounters a line which is bigger than its limit? getLine works safely, in that it stops collecting when the array is full, even if no new line has been seen. By testing the length and the last character returned, main can determine whether the line was too long, and then cope as it wishes. In the interests of brevity, we have ignored this issue. There is no way for a user of getLine to know in advance how long an input line might be, so getLine checks for overflow. On the other hand, the user of copy already knows or can find out how big the strings are, so we have chosen not to add error checking to it. Exercise 1-16. Revise the main routine of the longest line program so it will correctly print the length of arbitrary long input lines and as much as possible of the text. Exercise 1-17. Write a program to print all input lines that are longer than 80 characters. Exercise 1-18. Write a program to remove trailing blanks and tabs from each line of input and to delete entirely blank lines. Exercise 1-19. Write a function that reverses the character string s. Use it to write a program that reverses its input a line at a time. 1.10 External variables and scope. The variables in such as etc. are private or local to because they main line longest main are declared within main. No other function can have direct access to them. The same is true of the variables in other functions. For example, the variable I in getLine is unrelated to the I in copy. Each local variable in a function comes into existence only when the function is called and disappears when the function is exited. This is why such variables are usually known as automatic variables, following terminology in other languages. We will use the term automatic henceforth to refer to these local variables. Chapter 4 discusses the static storage class, in which local variables do retain their values between calls. Because automatic variables come and go with function invocation, they do not retain their values from one call to the next and must be explicitly set upon each entry. If they are not set, they will contain garbage. As an alternative to automatic variables, it is possible to define variables that are external to all functions, that is, variables that can be accessed by name by any function. This mechanism is rather like Fortran common or Pascal variables declared in the outermost block. Because external variables are globally accessible, they can be used instead of argument lists to communicate data between functions. Furthermore, because external variables remain in existence permanently, rather than appearing and disappearing as functions are called and exited, they retain their values even after the functions that set them have returned. An external variable must be defined exactly once outside of any function. This sets aside storage for it. The variable must also be declared in each function that wants to access it. This states the type of the variable. The declaration may be an explicit extern statement or may be implicit from context. To make the discussion concrete, let us rewrite the longest line program with line, longest, and max as external variables. This requires changing the calls, declarations, and bodies of all three functions. Hashtag includes dio, hashtag define maxline 1000 * maximum input line size * int max / maximum length seen so far / charline maxline / current input line / char longest maxline / longest line saved here * and get line void copy void * print longest input line specialized version * main int len extern at max extern char longest max equals 0 while len equals get line 0 if len max equals len copy. If max 0 / there is a line * printf %s longest return 0 * get line specialized version * and get line void int c I extern char line for I equals 0 I max line 1 and c equals get char equals eof and c equals \n plus I line I equals c if c equals \n align I equals c plus I align I equals \0 return I / copy specialized version * void copy void in I extern char line longest I equals 0 while longest I equals line I equals \0 plus I. The external variables in main, get line, and copy are defined by the first lines of the example above, which state their type and cause storage to be allocated for them. Syntactically, external definitions are just like definitions of local variables, but since they occur outside of functions, the variables are external. Before a function can use an external variable, the name of the variable must be made known to the function. The declaration is the same as before except for the added keyword extern. In certain circumstances, the extern declaration can be omitted. If the definition of the external variable occurs in the source file before its use in a particular function, then there is no need for an extern declaration in the function. The extern declarations in main, getLine, and copy are thus redundant. In fact, common practice is to place definitions of all external variables at the beginning of the source file, and then omit all extern declarations. If the program is in several source files, and a variable is defined in File 1 and used in File 2 and File 3, then extern declarations are needed in File 2 and File 3 to connect the occurrences of the variable. The usual practice is to collect extern declarations of variables and functions in a separate file, historically called a header, that is included by #include at the front of each source file. The suffix -h is conventional for header names. The functions of the standard library, for example, are declared in headers like stdio.h. This topic is discussed at length in Chapter 4, and the library itself in Chapter 7 and Appendix B. Since the specialized versions of and have no arguments, logic would suggest getLine copy that their prototypes at the beginning of the file should be, but for getLine copy. Compatibility with older C programs. The standard takes an empty list as an old-style declaration and turns off all argument list checking. The word void must be used for an explicitly empty list. We will discuss this further in Chapter 4. You should note that we are using the words definition and declaration carefully when we refer to external variables in this section. Definition refers to the place where the variable is created. Or assigned storage. Declaration refers to places where the nature of the variable is stated but no storage is allocated. By the way, there is a tendency to make everything in sight an extern variable because it appears to simplify communications. Argument lists are short, and variables are always there when you want them. But external variables are always there even when you don't want them. Relying too heavily on external variables is fraught with peril since it leads to programs whose data connections are not all obvious. Variables can be changed in unexpected and even inadvertent ways, and the program is hard to modify. The second version of the longest line program is inferior to the first, partly for these reasons, and partly because it destroys the generality of two useful functions by writing into them the names of the variables they manipulate. At this point, we have covered what might be called the conventional core of C. With this handful of building blocks, it's possible to write useful programs of considerable size, and it would probably be a good idea if you paused long enough to do so. These exercises suggest programs of somewhat greater complexity than the ones earlier in this chapter. Exercise 1-20. Write a program to tab that replaces tabs in the input with the proper number of blanks to space to the next tab stop. Assume a fixed set of tab stops, say every n columns. Should n be a variable or a symbolic parameter? Exercise 1-21. Write a program in tab that replaces strings of blanks by the minimum number of tabs and blanks to achieve the same spacing. Use the same tab stops as for to tab. When either a tab or a single blank would suffice to reach a tab stop, which should be given preference. Exercise 1-22. Write a program to fold long input lines into two or more shorter lines after the last non-blank character that occurs before the nth column of input. Make sure your program does something intelligent with very long lines, and if there are no blanks or tabs before the specified column. Exercise 1-23. Write a program to remove all comments from a C program. Don't forget to handle quoted strings and character constants properly. C comments don't nest. Exercise 1-24. Write a program to check a C program for rudimentary syntax errors like unmatched parentheses, brackets, and braces. Don't forget about quotes, both single and double, escape sequences, and comments. This program is hard if you do it in full generality. Chapter 2. Types, Operators, and Expressions. Variables and constants are the basic data objects manipulated in a program. Declarations list the variables to be used and state what type they have and perhaps what their initial values are. Operators specify what is to be done to them. Expressions combine variables and constants to produce new values. The type of an object determines the set of values it can have and what operations can be performed on it. These building blocks are the topics of this chapter. The ANSI standard has made many small changes and additions to basic types and expressions. There are now signed and unsigned forms of all integer types and notations for unsigned constants and hexadecimal character constants. Floating point operations may be done in single precision. There is also a long double type for extended precision. String constants may be concatenated at compile time. Enumerations have become part of the language, formalizing a feature of long standing. Objects may be declared const, which prevents them from being changed. The rules for automatic coercions among arithmetic types have been augmented to handle the richer set of types. 2.1 Variable names.
Although we didn't say so in Chapter 1, there are some restrictions on the names of variables.
Although we didn't say so in Chapter 1, there are some restrictions on the names of variables and symbolic constants. Names are made up of letters and digits. The first character must be a letter. The underscore counts as a letter. It is sometimes useful for improving the readability of long variable names. Don't begin variable names with underscore, however, since library routines often use such names. Upper and lowercase letters are distinct, so X and X are two different names. Traditional C practice is to use lowercase for variable names and all uppercase for symbolic constants. At least the first 31 characters of an internal name are significant. For function names and external variables, the number may be less than 31 because external names may be used by assemblers and loaders over which the language has no control. For external names, the standard guarantees uniqueness only for 6 characters and a single case. Keywords like if, else, int, float, etc. are reserved. You can't use them as variable names. They must be in lowercase. It's wise to choose variable names that are related to the purpose of the variable and that are unlikely to get mixed up typographically. We tend to use short names for local variables, especially loop indices, and longer names for external variables. 2.2 Data types and sizes. There are only a few basic data types in C. Char, a single byte, capable of holding one character in the local character set in an integer, typically reflecting the natural size of integers on the host machine. Float, single precision floating point, double precision floating point. In addition, there are a number of qualifiers that can be applied to these basic types. Short and long apply to integers. Short int sh, long int counter. The word int can be omitted in such declarations, and typically it is. The intent is that and should provide different lengths of integers where practical. Short-long will normally be the natural size for a particular machine. Is often 16 bits long, and int short in either 16 or 32 bits. Each compiler is free to choose appropriate sizes for its own hardware, subject only to the restriction that shorts and ints are at least 16 bits, longs are at least 32 bits. And short is no longer than int, which is no longer than long. The qualifier or may be applied to or any integer. Numbers signed in sign char and signed are always positive or 0 and obey the laws of arithmetic modulo 2n, where n is the number of bits in the type. So, for instance, if chars are 8 bits and sign char variables have values between 0 and 255, while sign chars have values between -128 and 127 in a choose complement machine. Whether plain chars are signed or unsigned is machine-dependent, but printable characters are always positive. The type long double specifies extended precision floating point. As with integers, the sizes of floating point objects are implementation defined. Float, double, and long double could represent 1, 2, or 3 distinct sizes. The standard headers and contain symbolic constants for all of these limits, h float, h sizes, along with other properties of the machine and compiler. These are discussed in Appendix B. Exercise 2-1. Write a program to determine the ranges of char, short, int, and long variables, both and by printing appropriate values from standard headers signed unsigned, and by direct computation. Harder if you compute them. Determine the ranges of the various floating point types. 2.3 Constants. An integer constant like is an a constant is written with a terminal L, or L, 1234 int. long as in an integer constant too big to fit into and will also be taken as a long. 1, 2, 3, 4, 5, 6, 7, 8, 9 L. Int and signed constants are written with a terminal U or U, and the suffix or indicates all UL and sign long. Floating point constants contain a decimal point or an exponent or both. They're 123.4. 1 times 10 to the power of -2 type is unless suffixed. The suffixes F or F indicate a constant. L or L indicate a double, float long double. The value of an integer can be specified in octal or hexadecimal instead of decimal. A leading 0, 0, on an integer constant means octal. A leading 0x or 0x means hexadecimal. For example, decimal 31 can be written as 037 in octal and 0x1f or 0x1f in hex. Octal and hexadecimal constants may also be followed by L to make them long and U to make them unsigned. 0xful is an unsigned long constant with value 15 decimal. A character constant is an integer written as one character within single quotes, such as x. The value of a character constant is the numeric value of the character in the machine's character set. For example, in the ASCII character set, the character constant, 0, has the value 48, which is unrelated to the numeric value 0. If we write 0, instead of a numeric value like 48 that depends on the character set, the program is independent of the particular value and easier to read. Character constants participate in numeric operations just as any other integers, although they are most often used in comparisons with other characters. Certain characters can be represented in character and string constants by escape sequences like \n newline. These sequences look like two characters, but represent only one. In addition, an arbitrary byte-sized bit pattern can be specified by \000, where 000 is 1 to 3 octal digits, 0, 7, or by \xhh, where HH is 1 or more hexadecimal digits, 0, 9, AF. So we might write #define VTAB \013 / ASCII vertical tab / #define bell \007 / ASCII bell character * or in hexadecimal. #define VTAB \xb / ASCII vertical tab / #define bell \x7 / ASCII bell character * the complete set of escape sequences is \alert bell character \\\\\\\, be backspace \, question mark. \f form feed \, single quote \, and new line \, double quote \, are carriage return \, 000 octal number \, t, horizontal tab \, xhh hexadecimal number \, v vertical tab. The character constant \0 represents the character with value 0, the null character. \0 is often written instead of 0 to emphasize the character nature of some expression, but the numeric value is just 0. A constant expression is an expression that involves only constants. Such expressions may be evaluated at during compilation rather than runtime, and accordingly may be used in any place that a constant can occur, as in #define maxline 1000 charline, maxline +1, or #define leap1 * in leap years * in days 31 plus 28 plus leap plus 31 plus 30 plus 31 plus 30 plus 31 plus 31 plus 30 plus 31 plus 30 plus 31. A string constant, or string literal, is a sequence of 0 or more characters surrounded by double quotes, as in, I am a string, or / the empty string * the quotes are not part of the string, but serve only to delimit it. The same escape sequences used in character constants apply in strings. / represents the double quote character. String constants can be concatenated at compile time. Hello, world is equivalent to hello, world. This is useful for splitting up long strings across several source lines. Technically, a string constant is an array of characters. The internal representation of a string has a null character, \0, at the end, so the physical storage required is one more than the number of characters written between the quotes. This representation means that there is no limit to how long a string can be, but programs must scan a string completely to determine its length. The standard library function stulens returns the length of its character string argument s, excluding the terminal \0. Here is our version. /*stulen, return length of s */int stulen char s in I, while s I equals \0 ++ I, return I, a and other string functions are declared in the standard header stulen stringed h. Be careful to distinguish between a character constant and a string that contains a single character. X is not the same as x. The former is an integer used to produce the numeric value of the letter X in the machine's character set. The latter is an array of characters that contains one character, the letter X, and a \0. There is one other kind of constant, the enumeration constant. An enumeration is a list of constant integer values, as in enum boolean no, yes, the first name in an enum has value 0, the next one, and so on, unless explicit values are specified. If not all values are specified, unspecified values continue the progression from the last specified value, as the second of these examples. Enum escape spell equals \a, backspace equals \b, tab equals \t, newline equals \n, vtab equals \v, return equals \r. Enomonless, yenedimein, ifb, emma, apr, me, Yun, Jul, AG, SIP, OCT, NOE, DEC, stjerne FB er lige med 2, MR er lige med 3, etc. stjerne. Names in different enumerations must be distinct. Values need not be distinct in the same enumeration. Enumerations provide a convenient way to associate constant values with names, an alternative to #define with the advantage that the values can be generated for you. Although variables of enum types may be declared, compilers need not check that what you store in such a variable is a valid value for the enumeration. Nevertheless, enumeration variables offer the chance of checking and so are often better than #defines. In addition, a debugger may be able to print values of enumeration variables in their symbolic form. 2.4 Declarations. All variables must be declared before use, although certain declarations can be made implicitly by content. A declaration specifies a type and contains a list of one or more variables of that type, as in int lower, upper, step. Char C, line 1000. Variables can be distributed among declarations in any fashion. The lists above could well be written as int lower, int upper, int step, char C, char line 1000. The latter form takes more space, but is convenient for adding a comment to each declaration for subsequent modifications. A variable may also be initialized in its declaration. If the name is followed by an equal sign and an expression, the expression serves as an initializer, as in char esc equals \\, single quote semicolon and I equals 0, int limit equals maxline +1, float eps equals 1.0 times 10 to the power of -5. If the variable in question is not automatic, the initialization is done once only, conceptually before the program starts executing, and the initializer must be a constant expression. An explicitly initialized automatic variable is initialized each time the function or block it is in is entered. The initializer may be any expression. External and static variables are initialized to 0 by default. Automatic variables for which is no explicit initializer have undefined, i.e., garbage, values. The qualifier const can be applied to the declaration of any variable to specify that its value will not be changed. For an array, the const qualifier says that the elements will not be altered. Const =e equals 2.7182818284595. Const char message equals warning. The const declaration can also be used with array arguments to indicate that the function does not change that array. int strlen const char. The result is implementation defined if an attempt is made to change a constant 2.5 arithmetic operators. The binary arithmetic operators are plus, dash, asterisk, / and the modulus operator %. Integer division truncates any fractional part, the expression x%y produces the remainder when x is divided by y, and thus is 0 when y divides x exactly. For example, a year is a leap year if it is divisible by 4 but not by 100, except that years divisible by 400 are leap years. Therefore, if year %4 equals 0 and year %100 is not equal to 0, year %400 equals 0, printf, %d is a leap year / n year, else printf, %d is not a leap year / n year. The % operator cannot be applied to a float or double. The direction of truncation / and the sign of the result 4% are machine-dependent for negative operands, as is the action taken on overflow or underflow. The binary plus and operators have the same precedence, which is lower than the precedence of asterisk, / and %, which is in turn lower than unary plus and dash. Arithmetic operators associate left to right. Table 2.1 at the end of this chapter summarizes precedence and associativity for all operators. 2.6 Relational and logical operators. The relational operators are equals. They all have the same precedence. Just below them in precedence are the equality operators. Equals. Relational operators have lower precedence than arithmetic operators, so an expression like I lim 1 is taken as I lim 1, as would be expected. More interesting are the logical operators and. Expressions connected by and or are evaluated left to right, and evaluation stops as soon as the truth or falsehood of the result is known. Most C programs rely on these properties. For example, here is a loop from the input function getLine that we wrote in Chapter 1. For I equals 0, I lim 1 and C equals getchar equals / n and C equals EOF plus I s I equals C. Before reading a new character, it is necessary to check that there is room to store it in the array S, so the test I lim 1 must be made first. Moreover, if this test fails, we must not go on and read another character. Similarly, it would be unfortunate if C were tested against before is called. EOF getchar, therefore the call and assignment must occur before the character in C is tested. The precedence of and is higher than that of, and both are lower than relational and equality operators, so expressions like I lim 1 and C equals getchar equals / n and C equals EOF need no extra parentheses. But since the precedence of equals is higher than assignment, parentheses are needed in C equals getchar equals / n to achieve the desired result of assignment to C and then comparison with / n. By definition, the numeric value of a relational or logical expression is 1 if the relation is true and 0 if the relation is false. The unary negation operator converts a non-zero operand into 0 and a 0 operand in 1. A common use of is in constructions like if valid rather than. If valid equals 0, it's hard to generalize about which form is better. Constructions like valid read nicely if not valid, but more complicated ones can be hard to understand. Exercise 2-2. Write a loop equivalent to the for loop above without using and or. 2.7 Type conversions. When an operator has operands of different types, they are converted to a common type according to a small number of rules. In general, the only automatic conversions are those that convert a narrower operand into a wider one without losing information, such as converting an integer into floating point in an expression like f plus I. Expressions that don't make sense, like using a float as a subscript, are disallowed. Expressions that might lose information, like assigning a longer integer type to a shorter or a floating point type to an integer, may draw a warning, but they are not illegal. A is just a small integer, so may be freely used in arithmetic expressions. This chars permits considerable flexibility in certain kinds of character transformations. One is exemplified by this naive implementation of the function atwa, which converts a string of digits into its numeric equivalent, /*atwa. Convert s to integer */ int atwa, char s, int I, n equals 0, for I equals 0, s I equals 0, and s I equals 9, plus I, n equals 10 * n plus s I 0, return n, as we discussed in Chapter 1, the expression s I 0 gives the numeric value of the character stored in because the values of 0, etc., s I 1 form a contiguous increasing sequence. Another example of to conversion is the function which maps a single char int lower character to lowercase for the ASCII character set. If the character is not an uppercase letter, lower returns it unchanged. / lower. Convert C to lowercase. ASCII only * int lower, int C. If C equals a and C equals C, return C plus a, else. Return C.
This works for ASCII because corresponding uppercase and lower.
This works for ASCII because corresponding uppercase and lowercase letters are a fixed distance apart as numeric values and each alphabet is contiguous. There is nothing but letters between A and Z. This latter observation is not true of the EBCDIC character set, however, so this code would convert more than just letters in EBCDIC. The standard header, typed H, described in Appendix B, defines a family of functions that provide tests and conversions that are independent of character set. For example, the function tolower is a portable replacement for the function lower shown above. Similarly, the test C equals 0 and C equals 9 can be replaced by isdigit C. We will use the typed H functions from now on. There is one subtle point about the conversion of characters to integers. The language does not specify whether variables of type char are signed or unsigned quantities. When a char is converted to an int, can it ever produce a negative integer? The answer varies from machine to machine, reflecting differences in architecture. On some machines, a char whose leftmost bit is 1 will be converted to a negative integer, sign extension. On others, a char is promoted to an int by adding zeros at the left end, and thus is always positive. The definition of C guarantees that any character in the machine's standard printing character set will never be negative, so these characters will always be positive quantities in expressions. But arbitrary bit patterns stored in character variables may appear to be negative on some machines, yet positive on others. For portability, specify signed or unsigned if non-character data is to be stored in char variables. Relational expressions like I greater than j and logical expressions connected by and are defined to have value 1 if true and 0 if false. Thus the assignment D equals C equals 0 and C equals 9 sets D to 1 if C is a digit and 0 if not. However, functions like may return isdigit for true. In the test part of if, while for etc. true just means non-zero, so this makes no difference. Implicit arithmetic conversions work much as expected. In general, if an operator like plus or asterisk that takes 2 operands, a binary operator, has operands of different types, the lower type is promoted to the higher type before the operation proceeds. The result is of the integer type. Section 6 of Appendix A states the conversion rules precisely. If there are no unsigned operands, however, the following informal set of rules will suffice. If either operand is convert the other to a long double. Otherwise, if either operand is convert the other to double. Otherwise, if either operand is convert the other to float. Otherwise, convert and to int. Char short then if either operand is convert the other to long. Notice that in an expression are not automatically converted to this is a floats double, change from the original definition. In general, mathematical functions like those in math.h will use double precision. The main reason for using float is to save storage in large arrays or, less often, to save time on machines where double precision arithmetic is particularly expensive. Conversion rules are more complicated when unsigned operands are involved. The problem is that comparisons between signed and unsigned values are machine-dependent because they depend on the sizes of the various integer types. For example, suppose that int is 16 bits and long is 32 bits. Then -1L less than 1U, because 1U, which is an unsigned int, is promoted to assign long. But -1L greater than 1UL because -1L is promoted to unsigned long and thus appears to be a large positive number. Conversions take place across assignments. The value of the right side is converted to the type of the left, which is the type of the result. A character is converted to an integer, either by sign extension or not, as described above. Longer integers are converted to shorter ones or to chars by dropping the excess high-order bits.
Thus in
int I, char c, I equals c, c equals I, the value of c is unchanged. This is true whether or not sign extension is involved. Reversing the order of assignments might lose information, however. If x is and I is, then xi and ix both cause conversions. To int causes float int, equals float truncation of any fractional part. When it is converted to whether the value is double float, rounded, or truncated is implementation dependent. Since an argument of a function call is an expression, type conversion also takes place when arguments are passed to functions. In the absence of a function prototype, char and short become int, and float becomes double. This is why we have declared function arguments to be int and double even when the function is called with char and float. Finally, explicit type conversions can be forced, coerced, in any expression with a unary operator called a cast. In the construction, type name, expression. The expression is converted to the name type by the conversion rules above. The precise meaning of a cast is as if the expression were assigned to a variable of the specified type, which is then used in place of the whole construction. For example, the library routine sqrt expects a double argument and will produce nonsense if inadvertently handled something else. Sqrt is declared in math h. So if n is an integer, we can use sqrt double n to convert the value of n to before passing it to note that the cast produces the double sqrt value of n in the proper type. N itself is not altered. The cast operator has the same high precedence as other unary operators, as summarized in the table at the end of this chapter. If arguments are declared by a function prototype, as the normally should be, the declaration causes automatic coercion of any arguments when the function is called. Thus, given a function prototype for sqrt, double, the call root 2 equals sqrt, 2, coerces the integer 2 into the value without any need for a cast. Double 2.0. The standard library includes a portable implementation of a pseudo-random number generator and a function for initializing the seed. The former illustrates a cast, and signed long int next equals 1. / rand. Returns pseudo-random integer on 0, 32767 * int rand, void. A next equals next * 110, 351, 5245 plus 12,345. Return and signed int. Next / 65536, % 32,768. * rand, set seed for rand. * /void srand, and signed in seed. Next equals seed. Exercise 2-3. Write a function toys, which converts a string of hexadecimal digits, including an optional 0x or 0x, into its equivalent integer value. The allowable digits are 0 through 9, A through F and A through F, 2.8 increment and decrement operators. C provides two unusual operators for incrementing and decrementing variables. The increment operator ++ adds 1 to its operand, while the decrement operator subtracts 1. We have frequently used ++ to increment variables, as in if C == \n++ NL, The unusual aspect is that and may be used either as prefix operators before the plus plus, variable as in or postfix operators after the variable. In both cases, the effect is to plus plus n plus plus. Increment n. But the expression increments n before its value is used, while plus plus n plus plus increments n after its value has been used. This means that in a context where the value is being used, not just the effect, plus plus n and n plus plus are different. If n is 5, then x equals n plus plus, sets x to 5, but x equals plus plus n. Sets x to 6. In both cases, n becomes 6. The increment and decrement operators can only be applied to variables. An expression like I plus j plus plus is illegal. In a context where no value is wanted, just the incrementing effect, as in if c equals backslash n, nl plus plus. Prefix and postfix are the same, but there are situations where one or the other is specifically called for. For instance, consider the function squeeze s, c, which removes all occurrences of the character c from the string s, / squeeze. Delete all c from s * void squeeze, char s, int c, int I, j. For I equals j equals 0, s I equals backslash 0, I plus plus if s, I equals c s, j plus plus equals s, I, s j equals backslash 0. Each time a non-c occurs, it is copied into the current j position, and only then is j increment to be ready for the next character. This is exactly equivalent to if s, I equals c, s, j equals s, I, j plus plus. Another example of a similar construction comes from the getLine function that we wrote in Chapter 1, where we can replace if c equals backslash n, s, I equals c plus plus I by the more compact if c equals backslash n, s, I plus plus equals c. As a third example, consider the standard function strcat s, t, which concatenates the string t to the end of string s. Assumes that there is enough space in s to hold the strcat combination. As we have written it, strcat returns no value. The standard library version returns a pointer to the resulting string. / strcat. Concatenate t to end of s. S must be big enough */ void strcat. Char s, char t, int I, j. I equals j equals 0, while s, I equals backslash 0, / find end of s / I plus plus, while s I plus plus equals t j plus plus equals backslash 0 / copy t */. Thus, each member is copied from t to s. The postfix plus plus is applied to both I and j to make sure that they are in position for the next pass through the loop. Exercise 2-4. Write an alternative version of squeeze, s1, s2, that deletes each character in s1 that matches any character in the string s2. Exercise 2-5. Write the function any s1, s2, which returns the first location in a string s1 where any character from the string s2 occurs, or -1 if s1 contains no characters from s2. The standard library function strpbrk does the same job but returns a pointer to the location. 2.9 Bitwise operators. C provides 6 operators for bit manipulation. These may only be applied to integral operands, that is, and whether signed or unsigned. Char, short, int, long, and bitwise inclusive or bitwise exclusive or left shift, right shift one's complement, unary. The bitwise an operator and is often used to mask off some set of bits. For example, n equals n and 0177 sets to 0 all but the low-order 7 bits of n. The bitwise or operator is used to turn bits on x equals x set underscore on, sets to 1 in x the bits that are set to 1 in set underscore on. The bitwise exclusive or operator sets a 1 in each bit position where its operands have different bits, and 0 where they are the same. One must distinguish the bitwise operators and from the logical operators and. which imply left-to-right evaluation of a truth value. For example, if x is 1 and y is 2, then x and y is 0 while x and y is 1. The shift operators and perform left and right shifts of their left operand by the number of bit positions given by the right operand, which must be non-negative. Thus x, 2 shifts the value of x by 2 positions, filling vacated bits with 0. This is equivalent to multiplication by 4. Right shifting an assigned quantity always fits the vacated bits with 0. Right shifting assigned quantity will fill with bit signs, arithmetic shift, on some machines and with 0 bits, logical shift, on others. The unary operator yields the ones complement of an integer, that is, it converts each 1 bit into a 0 bit and vice versa. For example, x equals x and 077 sets the last 6 bits of x to 0. Note that x is independent of word length and is and 077 thus preferable to, for example, x and 017, 7700, which assumes that x is a 16-bit quantity. The portable form involves no extra cost, since 077 is a constant expression that can be evaluated at compile time. As an illustration of some of the bit operators, consider the function getBits, x, p, n that returns the right-adjusted n-bit field of x that begins at position p. We assume that bit position 0 is at the right end and that n and p are sensible positive values. For example, getBits x 4, 3 returns the 3 bits in positions 4, 3, and 2, right-adjusted. / getBits get n bits from position p * and sign getBits and signed x int p int n. Return x, p plus 1, n, and 0, n. The expression x, p plus 1, n, moves the desired field to the right end of the word. 0 is all 1 bits. Shifting it left n positions with 0, n places zeros in the rightmost n bits, complementing that with makes a mask with 1s in the rightmost n bits. Exercise 2-6. Write a function set bits, x, p, n, y, that returns x with the n bits that begin at position p set to the rightmost n bits of y, leaving the other bits unchanged. Exercise 2-7. Write a function invert, x, p, n, that returns x with the n bits that begin at position p inverted, i.e., 1 changed into 0 and vice versa, leaving the others unchanged. Exercise 2-8. Write a function rightRot, x, n that returns the value of the integer x rotated to the right by n positions. 2.10 assignment operators and expressions such as I equals I plus 2, in which the variable on the left side is repeated immediately on the right, can be written in the compressed form I plus equals 2. The operator plus equals is called an assignment operator. Most binary operators like plus that have a left and right operand, have a corresponding assignment operator op equals, where op is one of plus, */%, and caret. If x per 1 and x per 2 are expressions, then x per 1 op equals x per 2 is equivalent to x per 1 equals x per 1 op x per 2, except that x per 1 is computed only once. Notice the parentheses around x per 2 x * equals y plus 1 means x equals x * y plus 1. Rather than x equals x * y plus 1 as an example, the function bitCount counts the number of 1 bits in its integer argument. /*bitCount. Count 1 bits in x * and bitCount and signed x, lint b. 4 b equals 0, x equals 0, x equals 1, if x and 0, 1, b++, return b. Declaring the argument x to be n and signed ensures that when it is right-shifted, vacated bits will be filled with zeros, not signed bits, regardless of the machine the program is run on. Quite apart from conciseness, assignment operators have the advantage that they correspond better to the way people think. We say add 2 to I, or increment I by 2, not take I, add 2, then put the result back in I. Thus the expression I plus equals 2 is preferable to I equals I plus 2. In addition, for a complicated expression like YYPV, YYPV, P3 plus P4 plus YYPV, P1 plus equals 2, the assignment operator makes the code easier to understand, since the reader doesn't have to check painstakingly that two long expressions are indeed the same, or to wonder why they're not. And an assignment operator may even help a compiler to produce efficient code. We have already seen that the assignment statement has a value and can occur in expressions. The most common example is while C equals getchar equals EOF. The other assignment operators, plus equals, dash equals, etc., can also occur in expressions, although this is less frequent. In all such expressions, the type of an assignment expression is the type of its left operand, and the value is the value after the assignment. Exercise 2-9. In a 2's complement number system, x and equals x1 deletes the rightmost 1 bit in x. Explain why. Use this observation to write a faster version of bit count. 2.11 conditional expressions. The statements: if A greater than B, Z equals A, else C equals B. Compute in Z the maximum of A and B. The conditional expression, written with a ternary operator, colon, provides an alternate way to write this and similar constructions. In the expression
XPR à XPR 2 d'XPR 3,
the expression x per 1 is evaluated first. If it is non-zero, true, then the expression x per 2 is evaluated, and that is the value of the conditional expression. Otherwise, x per 3 is evaluated, and that is the value. Only one of x per 2 and x per 3 is evaluated. Thus, to set z to the maximum of A and B, z equals A greater than B. A, B, / z equals max, A, B, */ it should be noted that the conditional expression is indeed an expression, and it can be used wherever any other expression can be. If x per 2 and x per 3 are of different types, the type of the result is determined by the conversion rules discussed earlier in this chapter. For example, if f is a float and n an int, then the expression n greater than 0, f, and is of type float regardless of whether n is positive. Parentheses are not necessary around the first expression of a conditional expression, since the precedence of is very low, just above assignment. They are advisable anyway, however, since they make the condition part of the expression easier to see. The conditional expression often leads to succinct code. For example, this loop prints n elements of an array, 10 per line, with each column separated by one blank, and with each line, including the last, terminated by a new line. For I equals 0, I less than n, I plus plus, printf, %6d%c, I %10 equals 9 I equals n1, \n, a new line is printed after every 10th element and after the nth. All other elements are followed by one blank. This might look tricky, but it's more compact than the equivalent of else. Another good example is printf. You have %d items %s, \n, and n equals 1. S. Exercise 2-10. Rewrite the function lower, which converts uppercase letters to lowercase, with a conditional expression instead of if-else. 2.12 Precedence and order of evaluation. Table 2.1 summarizes the rules for precedence and associativity of all operators, including those that we have not yet discussed. Operators on the same line have the same precedence. Rows are in order of decreasing precedence, so, for example, asterisk, /, and % all have the same precedence, which is higher than that of binary plus and dash. The operator refers to function call. The operators dash and are used to access members of structures. They will be covered in Chapter 6, along with size of an object. Chapter 5 discusses asterisk, indirection through a pointer, and address of an object, and Chapter 3 discusses the comma operator, operators associativity, dash, left to right, plus, asterisk, type, size of right to left, asterisk, /% left to right plus, left to right, left to right equals left to right equals left to right and left to right caret left to right and left to right right to left plus dash asterisk forward slash percent and caret right to right unary and plus dash and asterisk have higher precedence than the binary forms. Table 2.1 Precedence and associativity of operators. Note that the precedence of the bitwise operators and caret and falls below and equals. This equals implies that bit testing expressions like if x and mask equals 0 must be fully parenthesized to give proper results. C, like most languages, does not specify the order in which the operands of an operator are evaluated. The exceptions are and, colon, and. For example, in a statement like x equals f plus g. F may be evaluated before g or vice versa. Thus, if either f or g alters a variable on which the other depends, x can depend on the order of evaluation. Intermediate results can be stored in temporary variables to ensure a particular sequence. Similarly, the order in which function arguments are evaluated is not specified, so the statement printf %d \n ++n power 2n / wrong * can produce different results with different compilers, depending on whether n is increment before power is called. The solution, of course, is to write ++n printf %d \n and power 2n. Function calls, nested assignment statements, and increment and decrement operators cause side effects. Some variable is changed as a byproduct of the evaluation of an expression. In any expression involving side effects, there can be subtle dependencies on the order in which variables taking part in the expression are updated. One unhappy situation is typified by the statement I equals I++. The question is whether the subscript is the old value of I or the new. Compilers can interpret this in different ways and generate different answers depending on their interpretation. The standard intentionally leaves most such matters unspecified. When side effects, assignment to variables, take place within an expression is left to the discretion of the compiler, since the best order depends strongly on machine architecture. The standard does specify that all side effects on arguments take effect before a function is called, but that would not help in the call to printf above. The moral is that writing code that depends on order of evaluation is a bad programming practice in any language. Naturally, it is necessary to know what things to avoid, but if you don't know how they are done on various machines, you won't be tempted to take advantage of a particular implementation. Chapter 3: Control Flow. The control flow of a language specify the order in which computations are performed. We have already met the most common control flow constructions in earlier examples. Here we will complete the set and be more precise about the ones discussed before. 3.1 Statements and blocks. An expression such as x or becomes a statement when it is followed equals 0 I++ printf by a semicolon as an x equals 0 I++ printf. In C, the semicolon is a statement terminator rather than a separator as it is in languages like Pascal. Braces and are used to group declarations and statements together into a compound statement or block so that they are syntactically equivalent to a single statement. The braces that surround the statements of a function are one obvious example. Braces around multiple statements after an if, else, while, or for are another. Variables can be declared inside any block. We will talk about this in Chapter 4. There is no semicolon after the right brace that ends a block. 3.2 If-else. The if-else statement is used to express decisions. Formally, the syntax is if expression statement 1 else. Statement 2, where the else part is optional. The expression is evaluated. If it is true, that is, if expression has a non-zero value, statement 1 is executed. If it is false, expression is 0, and if there is an else part, statement 2 is executed instead. Since an if tests the numeric value of an expression, certain coding shortcuts are possible. The most obvious is writing if expression instead of if expression equals 0. Sometimes this is natural and clear, at other times it can be cryptic. Because the part of an is optional, there is an ambiguity when an else if omitted else if else from a nested if sequence. This is resolved by associating the with the closest previous else less if.
For example, in
If n greater than 0, if a greater than b, z equals a, else c equals b. The else goes to the inner if, as we have shown by indentation. If that isn't what you want, braces must be used to force the proper association. If n greater than 0, if a greater than b, z equals a, else c equals b, the ambiguity is especially pernicious in situations like this. If n greater than 0, for I equals 0, I less than n, I plus plus, if s, I 0, a printf, return I, else slash asterisk wrong asterisk slash printf, error, n is negative backslash n. The indentation shows unequivocally what you want, but the compiler doesn't get the message and associates the else with the inner if. This kind of bug can be hard to find. It's a good idea to use braces when there are nested ifs. By the way, notice that there is a semicolon after z equals n. If a greater than b, z equals a, else c equals b, this is because grammatically, a statement follows the if, and an expression statement like z equals a is always terminated by a semicolon. 3.3 Else if the construction. If expression, statement else if expression, statement else if expression, statement else if expression, statement else statement occurs so often that it is worth a brief separate discussion. This sequence of if statements is the most general way of writing a multi-way decision. The expressions are evaluated in order. If an expression is true, the statement associated with it is executed, and this terminates the whole chain. As always, the code for each statement is either a single statement or a group of them in braces. The last else part handles the none of the above, or default case, where none of the other conditions is satisfied. Sometimes there is no explicit action for the default. In that case, the trailing else statement can be omitted, or it may be used for error checking to catch an impossible condition. To illustrate a three-way decision, here is a binary search function that decides if a particular value x occurs in the sorted array V. The elements of V must be in increasing order. The function returns the position, a number between 0 and n1, if x occurs in V, and -1 if not. Binary search first compares the input value x to the middle element of the array V. If x is less than the middle value, searching focuses on the lower half of the table, otherwise on the upper half. In either case, the next step is to compare x to the middle element of the selected half. This process of dividing the range in two continues until the value is found or the range is empty. / bin search. Find x in V0 equals V1 equals V n1 * int bin search int x int V int n int low high mid. Low equals 0, high equals n1, while low equals high. Mid equals low plus high /2, if x less than v mid high equals mid plus 1, else if x greater than v mid, low equals mid plus 1, else * found match /return mid, return -1, no match */. The fundamental decision is whether x is less than, greater than, or equal to the middle element v, mid at each step. This is a natural for else if. Exercise 3-1. Our binary search makes two tests inside the loop, when one would suffice, at the price of more tests outside. Write a version with only one test inside the loop and measure the difference in runtime. 3.4 Switch. The switch statement is a multi-way decision that tests whether an expression matches one of a number of constant integer values and branches accordingly. Switch expression, a case const expr, statements case const expr, statements default, statements. Each case is labeled by one or more integer valued constants or constant expressions. If a case matches the expression value, execution starts at that case. All case expressions must be different. The case label default is executed if none of the other cases are satisfied. A default is optional. If it isn't there and if none of the cases match, no action at all takes place. Cases and the default clause can occur in any order. In Chapter 1, we wrote a program to count the occurrences of each digit, white space, and all other characters, using a sequence of if, else. Here is the same program with a switch. Hashtag includes diode, hmain, / count digits, white space, others * and c, ein white, another, digit 10, white equals another equals 0, for I equals 0, I less than 10, I plus, digit, I equals 0, while c equals get char, equals of. Switch C, a case 0, case 1, case 2, case 3, case 4, case 5, case 6, case 7, case 8, case 9, digit C-0, break, case \n, case \t, white break, default. Another break, printf, digits equals, for I equals 0, I less than 10, I plus. Printf, %d, digit I, printf, white space equals %d, other equals %d \n, white, another, return 0. The break statement causes an immediate exit from the because cases serve just as switch. Labels, after the code for one case is done, execution falls through to the next unless you take explicit action to escape. Break and return are the most common ways to leave a switch. A break statement can also be used to force an immediate exit from while, for, and do loops, as will be discussed later in this chapter. Falling through cases is a mixed blessing. On the positive side, it allows several cases to be attached to a single action, as with the digits in this example. But it also implies that normally each case must end with a break to prevent falling through to the next. Falling through from one case to another is not robust, being prone to disintegration when the program is modified. With the exception of multiple labels for a single computation, fall-throughs should be used sparingly and commented. As a matter of good form, put after the last case the here, even though its break default logically unnecessary. Someday when another case gets added at the end, this bit of defensive programming will save you. Exercise 3-2. Write a function escape, st, that converts characters like newline and tab into visible escape sequences like \n and \t as it copies the string t to s. Use a switch. Write a function for the other direction as well, converting escape sequences into the real characters. 3.5 loops, while, and for we have already encountered the and loops. In while for. While, expression statement. The expression is evaluated. If it is non-zero, statement is executed and expression is reevaluated. This cycle continues until expression becomes 0, at which point execution resumes after statement. The for statement. For exp1, exp2, exp3 statement is equivalent to exp1, while exp2. Statement exp3, except for the behavior of continue, which is described in section 3.7. Grammatically, the three components of a for loop are expressions. Most commonly, exp1 and exp3 are assignments or function calls, and exp2 is a relational expression. Any of the three parts can be omitted, although the semicolons must remain. If exp1 or exp3 is omitted, it is simply dropped from the expansion. If the test exp2 is not present, it is taken as permanently true, so for winky face is an infinite loop, presumably to be broken by other means, such as a or break return. Whether to use or is largely a matter of personal preference. For example, in while for. While C equals get char equals, C equals equals backslash N C equals backslash T forward slash asterisk skip white space characters asterisk slash. There is no initialization or reinitialization, so the while is most natural. The for is preferable when there is a simple initialization and increment, since it keeps the loop control statements close together and visible at the top of the loop.
This is most obvious in
For I equals 0, I less than n I plus plus, which is the C idiom for processing the first n elements of an array, the analog of the Fortran do loop or the Pascal for. The analogy is not perfect, however, since the index variable I retains its value when the loop terminates for any reason. Because the components of the for are arbitrary expressions, for loops are not restricted to arithmetic progressions. Nonetheless, it is bad style to force unrelated computations into the initialization and increment of a for, which are better reserved for loop control operations. As a larger example, here is another version of ATWA for converting a string to its numeric equivalent. This one is slightly more general than the one in Chapter 2. It copes with optional leading white space and an optional plus or sign. Chapter 4 shows a TOF, which does the same conversion for floating point numbers. The structure of the program reflects the form of the input: skip white space, if any, get sign, if any. Get integer part and convert it. Each step does its part and leaves things in a clean state for the next. The whole process terminates on the first character that could not be part of a number. Hashtag include type h / asterisk atwa. Convert s to integer. Version 2 / in atwa char s int I end sign for I equals 0 is space s I plus plus / skip white space asterisk / sign equals s I equals dash -11. If s I equals plus s I equals dash / asterisk skip sign asterisk / I plus plus. For n equals 0, istigit s I plus plus n equals 10 asterisk n plus s I 0. Return sign asterisk n. The standard library provides a more elaborate function strtl for conversion of strings to long integers. See Section 5 of Appendix B. The advantages of keeping loop control centralized are even more obvious when there are several nested loops. The following function is a shell sort for sorting an array of integers. The basic idea of this sorting algorithm, which was invented in 1959 by D.L. Shell, is that in early stages, far apart elements are compared, rather than adjacent ones as in simpler interchange sorts. This tends to eliminate large amounts of disorder quickly, so later stages have less work to do. The interval between compared elements is gradually decreased to 1, at which point the sort effectively becomes an adjacent interchange method. / shell sort v0, v and 1 into increasing order * void shell sort in v, in n, in gap ij temp for gap equals n/2, gap 0, gap / equals 2 for equals gap I less than n, I plus plus.
For je rovno I gap, je rovno 0 a av.
For j equals I gap, j and gt equals 0 and vj and gt vj plus gap, j equals gap, temp equals vj, vj equals vj plus gap, vj plus gap equals temp. There are 3 nested loops. The outermost controls the gap between compared elements, shrinking it from n/2 by a factor of 2 each pass until it becomes 0. The middle loop steps along the elements. The innermost loop compares each pair of elements that is separated by gap and reverses any that are out of order. Since gap is eventually
There are 3 nested loops.
There are 3 nested loops. The outermost controls the gap between compared elements, shrinking it from n/2 by a factor of 2 each pass until it becomes 0. The middle loop steps along the elements. The innermost loop compares each pair of elements that is separated by gap and reverses any that are out of order. Since gap is eventually reduced to 1, all elements are eventually ordered correctly. Notice how the generality of the for makes the outer loop fit in the same form as the others, even though it is not an arithmetic progression. One final C operator is the comma, which most often finds use in the statement. A for pair of expressions separated by a comma is evaluated left to right, and the type and value of the result are the type and value of the right operand. Thus, in a for statement, it is possible to place multiple expressions in the various parts, for example, to process two indices in parallel. This is illustrated in the function reverses, which reverses the string south in place. Hashtag include string h/*reverse, reverse string south in place */void reverse, char s, int c, I, j.
For I er lig med 0, j er lig med streg, s, 1, I er mindre end j, ik plus, j.
4, I equals 0, j equals strollen, s, 1, I and ltj, I plus plus, j, c equals si, si equals sj, sj equals c. The commas that separate function arguments, variables in declarations, etc., are not comma operators, and do not guarantee left-to-right evaluation. Comma operators should be used sparingly. The most suitable uses are for constructs strongly related to each other, as in the for loop in reverse, and in macros where a multi-step computation has to be a single expression. A comma expression might also be appropriate for the exchange of elements in reverse, where the exchange can be thought of a single operation. 4, I equals 0, j equals strollen, s, 1, I and ltj, I plus plus, j, c equals si, si equals sj, sj equals c, exercise 3-3.
For I er lig med 0, j er lig med streg.
3.6 loops.
For I er lig med 0, j er lig med streg, s, 1, I er mindre end j, ik plus, j, c er lig med s, I er lig med s, j er lig med c, exercise 3-3.
Write a function expand s1, s2 that expands shorthand notations like in AZ the string s1 into the equivalent complete list in s2. Allow for letters of either case ABC, XYZ, and digits, and be prepared to handle cases like ABC and arrange that AA, Z0-9, AZ, leading or trailing, is taken literally. 3.6 loops do while. As we discussed in Chapter 1, the in loops tests the termination condition at the while for top. By contrast, the third loop in C, the do while, tests at the bottom after making each pass through the loop body. The body is always executed at least once. The syntax of the do is do. Statement while, expression. The statement is executed, then expression is evaluated. If it is true, statement is evaluated again and so on. When the expression becomes false, the loop terminates. Except for the sense of the test, do while is equivalent to the Pascal repeat until statement. Experience shows that is much less used than and nonetheless from do while for. Time to time it is valuable, as in the following function idoa, which converts a number to a character string, the inverse of atwa. The job is slightly more complicated than might be thought at first, because the easy methods of generating the digits generate them in the wrong order. We have chosen to generate the string backwards, then reverse it. /* idoa. Convert n to characters in s/void idoa. Int n, char s, I and I sign if, sign equals n or 0, / record sign */ n equals n, /* make n positive /I equals 0. Do / generate digits in reverse order /s, I plus plus, equals n% 10 plus 0, / get next digit / while, n / equals 10 0, / delete it * if, sign 0, s, I plus plus, equals dash. S, I equals \0, reverses. The do while is necessary, or at least convenient, since at least one character must be installed in the array S, even if n is 0. We also used braces around the single statement that makes up the body of the do while, even though they are unnecessary. so the hasty reader will not mistake the while part for the beginning of a while loop. Exercise 3 to 4. In a 2's complement number representation, our version of EDOA does not handle the largest negative number, that is, the value of n equal to dash 2 word size 1. Explain why not. Modify it to print that value correctly, regardless of the machine on which it runs. Exercise 3 to 5. Write the function itob n s b that converts the integer n into a base b character representation in the string s. In particular, itob n s 16 formats s as a hexadecimal integer in s. Exercise 3 to 6. Write a version of EDOA that accepts 3 arguments instead of 2. The third argument is a minimum field width. The converted number must be padded with blanks on the left if necessary to make it wide enough. 3.7 break and continue. It is sometimes convenient to be able to exit from a loop other than by testing at the top or bottom. The break statement provides an early exit from for, while, and do, just as from switch. A break causes the innermost enclosing loop or switch to be exited immediately. The following function, trim, removes trailing blanks, tabs, and new lines from the end of a string, using a break to exit from a loop when the rightmost non-blank, non-tab, non-new line is found. / trim, remove trailing blanks, tabs, new lines */int trim, char s, in n for n equals len s, dash 1, n equals 0, n, if s n equals, and s and equals \t, and s n equals \n, break, s n plus 1 equals \0, return n. Returns the length of the string. The loop starts at the end and scans backwards to len for looking for the first character that is not a blank or tab or a new line. The loop is broken when 1 is found, or when n becomes negative, that is, when the entire string has been scanned. You should verify that this is correct behavior even when the string is empty or contains only white space characters. The statement is related to but less often used. It causes the next iteration of continue break, the enclosing or do loop to begin. In the end do, this means that the test for, while part is executed immediately. In the for, control passes to the increment step. The continue statement applies only to loops, not to switch. A continue inside a switch inside a loop causes the next loop iteration. As an example, this fragment processes only the non-negative elements in the array, and negative values are skipped. For I equals 0, I less than n, I plus plus if a I 0, / skip negative elements * continue. / do positive elements * the continue statement is often used when the part of the loop that follows is complicated, so that reversing a test and indenting another level would nest the program too deeply. 3.8 Goto and labels. C provides the infinitely abusable goto statement and labels to branch to. Formally, the goto statement is never necessary, and in practice it is almost always easy to write code without it. We have not used goto in this book. Nevertheless, there are a few situations where gotos may find a place. The most common is to abandon processing in some deeply nested structure, such as breaking out of 2 or more loops at once. The break statement cannot be used directly since it only exits from the innermost loop. Thus, for if disaster, goto error. Error / clean up the mess * this organization is handy if the error handling code is non-trivial and if errors can occur in several places. A label has the same form as a variable name and is followed by a colon. It can be attached to any statement in the same function as the goto. The scope of a label is the entire function. As another example, consider the problem of determining whether two arrays A and B have an element in common. One possibility is for I equals 0, I less than n, I plus plus for j equals 0, j less than m, j plus plus if a I equals b j. Goto found, / didn't find any common element / found / got one, a I equals b j */ Code involving a goto can always be written without one, though perhaps at the price of some repeated tests or an extra variable. For example, the array search becomes found equals 0 for I equals 0, I less than n and found I plus plus for j equals 0, j less than m and found j plus plus if ai equals bj, found equals 1 if found / got 1, ai 1 equals bj 1 * else / didn't find any common element *. With a few exceptions like those cited here, code that relies on goto statements is generally harder to understand and to maintain than code without gotos. Although we are not dogmatic about the matter, it does seem that goto statements should be used rarely, if at all. Chapter 4. Functions and Program Structure. Functions break large computing tasks into smaller ones and enable people to build on what others have done instead of starting over from scratch. Appropriate functions hide details of operation from parts of the program that don't need to know about them, thus clarifying the whole and easing the pain of making changes. C has been designed to make functions efficient and easy to use. C programs generally consist of many small functions rather than a few big ones. A program may reside in one or more source files. Source files may be compiled separately and loaded together, along with previously compiled functions from libraries. We will not go into that process here, however, since the details vary from system to system. Function declaration and definition is the area where the ANSI standard has made the most changes to C. As we saw first in Chapter 1, it is now possible to declare the type of arguments when a function is declared. The syntax of function declaration also changes so that declarations and definitions match. This makes it possible for a compiler to detect many more errors than it could before. Furthermore, when arguments are properly declared, appropriate type coercions are performed automatically. The standard clarifies the rules on the scope of names. In particular, it requires that there be only one definition of each external object. Initialization is more general. Automatic arrays and structures may now be initialized. The C preprocessor has also been enhanced. New preprocessor facilities include a more complete set of conditional compilation directives, a way to create quoted strings from macro arguments, and better control over the macro expansion process. 4.1 Basics of Functions. To begin with, let us design and write a program to print each line of its input that contains a particular pattern, or string of characters. This is a special case of the Unix program grep. For example, searching for the pattern of letters old in the set of lines. All love. Could you and I with fate conspire to grasp this sorry scheme of things entire? Would not we shatter it to bits, and then remold it nearer to the heart's desire? Will produce the output. All love. Could you and I with fate conspire? Would not we shatter it to bits, and then remold it nearer to the heart's desire? The job falls neatly into 3 pieces. While there's another line, if the line contains the pattern, print it. Although it's certainly possible to put the code for all of this in main, a better way is to use the structure to advantage by making each part a separate function. 3 small pieces are better to deal with than one big one, because irrelevant details can be buried in the functions, and the chance of unwanted interactions is minimized. And the pieces may even be useful in other programs.
While there's another line is getLine, a function that
While there's another line is getLine, a function that we wrote in Chapter 1, and printed is printf, which someone has already provided for us. This means we need only write a routine to decide whether the line contains an occurrence of the pattern. We can solve that problem by writing a function strindex, s, t, that returns the position or index in the string s where the string t begins, or -1 if S does not contain T. Because C arrays begin at position 0, indexes will be 0 or positive, and so a negative value like -1 is convenient for signaling failure. When we later need more sophisticated pattern matching, we only have to replace strindex. The rest of the code can remain the same. The standard library provides a function str that is similar to strindex, except that it returns a pointer instead of an index. Given this much design, filling in the details of the program is straightforward. Here is the whole thing so you can see how the pieces fit together. For now, the pattern to be searched for is a literal string, which is not the most general of mechanisms. We will return shortly to a discussion of how to initialize character arrays, and in Chapter 5 we'll show how to make the pattern a parameter that is set when the program is run. There is also a slightly different version of getLine. You might find it instructive to compare it to the one in Chapter 1. Hashtag includes diode. Hashtag define maxline 1000 / maximum input line length */ int getLine, charline, int max, int strindex, char source, char search for, char pattern equals old, / pattern to search for / find all lines matching pattern * main. Char line maxline int found equals 0, while getLine line maxline 0 if strindex line pattern equals 0, a printf %s line found ++, return found. / getLine, getLine into s, return length */ int getLine, char s, int lim, int c, I equals 0, while lim 0 and c equals getchar, equals eof and c equals \n, s I++ equals c, if c equals \n. s I++ equals c, s I equals \0, return I, / strindex, return index of t and s, -1 if none */ and strindex, char s, char t, int I, j, k.
For I er lig med 0, s og i er lig med 0, ikke plus, for j er lig med i.
4. I equals 0, si equals \0, I++, 4, j equals I, k equals 0, tk equals \0 and sj equals tk, j++, k++. If k and gt0 and ntk equals \0, return I, return -1. Each function definition has the form return type function name, argument declarations and statements. Various parts may be absent. A minimal function is dummy, which does nothing and returns nothing. A do-nothing
Dummy, which does nothing and returns nothing. A do-nothing function like this is sometimes useful as a placeholder during program development. If the return type is omitted, int is assumed. A program is just a set of definitions of variables and functions. Communication between the functions is by arguments and values returned by the functions and through external variables. The functions can occur in any order in the source file, and the source program can be split into multiple files, so long as no function is split. The return statement is the mechanism for returning a value from the called function to its caller. Any expression can follow return. Return expression. The expression will be converted to the return type of the function if necessary. Parentheses are often used around the expression, but they are optional. The calling function is free to ignore the return value. Furthermore, there need to be no expression after return. In that case, no value is returned to the caller. Control also returns to the caller with no value when execution falls off the end of the function by reaching the closing right brace. It is not illegal but probably a sign of trouble if a function returns a value from one place and no value from another. In any case, if a function fails to return a value, its value is certain to be garbage. The pattern searching program returns a status from main, the number of matches found. This value is available for use by the environment that called the program. The mechanics of how to compile and load a C program that resides on multiple source files vary from one system to the next. On the Unix system, for example, The CC command mentioned in Chapter 1 does the job. Suppose that the three functions are stored in three files called maind.c, getLine.c, and strindex.c. Then the command cc maind c getLine c strindex c compiles the three files, placing the resulting object code in files main.o, getLine.o, and then loads them all into an executable file called if there is an error. Say in strindex.o, it out. Maind.c, the file can be recompiled by itself and the result loaded with the previous object files with the command cc maind c getLine o strindex o. The cc command uses the c versus o naming convention to distinguish source files from object files. Exercise 4-1. Write the function strindex s t, which returns the position of the rightmost occurrence of t and s, or -1 if there is none. 4.2 Functions returning non-integers. So far our examples of functions have returned either no value or an what if a void int. Function must return some other type. Many numerical functions like sqrt, sine, and cosine return double. Other specialized functions return other types. To illustrate how to deal with this, let us write and use the function atovs, which converts the string s to its double precision floating point equivalent. Atov if an extension of atwa, which we showed versions of in chapters 2 and 3. It handles an optional sign and decimal point, and the presence or absence of either part or fractional part. Our version is not a high-quality input conversion routine. That would take more space than we care to use. The standard library includes an atov. The header stlib h declares it. First, itself must declare the type of value it returns, since it is not the type name atov int. Precedes the function name, hashtag include, typed h, / asterisk atov, convert string s to double atov, char s, double val, power, and I sign for I equals 0, space s, I plus plus, / skip white space asterisk / sign equals s, I equals dash. Mengjun, if, esa, I,
sign equals, si equals dash, -1, 1, if, si equals plus si equals dash, I plus plus, 4, val equals 0.0, istajit, si, I plus plus, val equals 10.0 asterisk val plus, si, 0, if, si equals dot, I plus plus. 4, power equals 1.0, istajit, si, I plus plus, val equals 10.0 asterisk val plus, si, 0, power asterisk equals 10. Return sign asterisk val / power, second, and just as important.
Return sign asterisk val / power, second, and just as important, the calling routine must know that atov returns a non-int value. One way to ensure this is to declare atov explicitly in the calling routine. The declaration is shown in this primitive calculator, barely adequate for checkbook balancing, which reads one number per line, optionally preceded with a sign, and adds them up. Printing the running sum after each input, hashtag include stiode, h, hashtag define maxline 100 / asterisk rudimentary calculator asterisk / main. Double sum, atov, char line maxline int getLine, char line, int max, sum equals 0, while getLine, line maxline 0, printf, \t% g \n sum plus equals atov, line, return 0. The declaration. Double sum, atov, char, says that sum is a double variable and that is a function that takes one argument atov char and returns a double. The function must be declared and defined consistently. If itself and the call to it in atov main have inconsistent types in the same source file, the error will be detected by the compiler. But if, as is more likely, atov were compiled separately, the mismatch would not be detected. Atov would return a double that main would treat as an int, and meaningless answers would result. In the light of what we have said about how declarations must match definitions, this might seem surprising. The reason a mismatch can happen is that if there is no function prototype, a function is implicitly declared by its first appearance in an expression such as sum plus equals a tof line. If a name that has not been previously declared occurs in an expression and is followed by a left parentheses, it is declared by context to be a function name. The function is assumed to return an int, and nothing is assumed about its arguments. Furthermore, if a function declaration does not include arguments, as in double a tof, that too is taken to mean that nothing is to be assumed about the arguments of a tof. All parameter checking is turned off. This special meaning of the empty argument list is intended to permit older C programs to compile with new compilers. But it's a bad idea to use it with new C programs. If the function takes arguments, declare them. If it takes no arguments, use void. Given properly declared, we could write convert a string to in terms of it. A tof @wyant / *@wa. Convert string s to integer using a tof * in @wa. Char s, double a tof, char s, return int to tovs. Notice the structure of the declarations and the return statement. The value of the expression in return expression is converted to the type of the function before the return is taken. Therefore, the value of a tof is converted automatically to when it appears in this, since the function double int returns in this operation does potentially discard information, however.
So sum @wyant.
Compilers warn of it. The cast states explicitly that the operation is intended and suppresses any warning. Exercise 4-2. Extend a tof to handle scientific notation of the form 123.45 times 10 to the power of -6, where a floating point number may be followed by e or e and an optionally signed exponent. For point 3 external variables. A C program consists of a set of external objects, which are either variables or functions. The adjective external is used in contrast to internal, which describes the arguments and variables defined inside functions. External variables are defined outside of any function and are thus potentially available to many functions. Functions themselves are always external because C does not allow functions to be defined inside other functions. By default, external variables and functions have the property that all references to them by the same name, even from functions compiled separately, are references to the same thing. The standard calls this property external linkage. In this sense, external variables are analogous to Fortran common blocks or variables in the outermost block in Pascal. We will see later how to define external variables and functions that are visible only within a single source file. Because external variables are globally accessible, they provide an alternative to function arguments and return values for communicating data between functions. Any function may access an external variable by referring to it by name, if the name has been declared somehow. If a large number of variables must be shared among functions, external variables are more convenient and efficient than long argument lists. As pointed out in Chapter 1, however, this reasoning should be applied with some caution, for it can have a bad effect on program structure and lead to programs with too many data connections between functions. External variables are also useful because of their greater scope and lifetime. Automatic variables are internal to a function. They come into existence when the function is entered and disappear when it is left. External variables, on the other hand, are permanent, so they can retain values from one function invocation to the next. Thus, if two functions must share some data, yet neither calls the other, it is often most convenient if the shared data is kept in external variables rather than being passed in and out via arguments. Let us examine this issue with a larger example. The problem is to write a calculator program that provides the operators plus, dash, asterisk, and slash. Because it is easier to implement, the calculator will use reverse Polish notation instead of infix. Reverse Polish notation is used by some pocket calculators and in languages like Forth and PostScript. In reverse Polish notation, each operator follows its operands, an infix expression like Open parenthesis 1 minus 2 close parenthesis times open parenthesis 4 plus 5 close parenthesis is entered as 1 2 2 4 5 plus asterisk parentheses are not needed. The notation is unambiguous as long as we know how many operands each operator expects. The implementation is simple. Each operand is pushed onto a stack. When an operator arrives, the proper number of operands, 2 for binary operators, is popped, the operator is applied to them, and the result is pushed back onto the stack. In the example above, for instance, 1 and 2 are pushed, then replaced by their difference, -1. Next, 4 and 5 are pushed, and then replaced by their sum, 9. The product of -1 and 9, which is -9, replaces them on the stack. The value on the top of the stack is popped and printed when the end of the input line is encountered. The structure of the program is thus a loop that performs the proper operation on each operator and operand as it appears, while next operator or operand is not end-of-file indicator, if, number. Push it else if, operator, pop operands do operation push result else if, new line, pop, and print top of stack else error. The operation of pushing and popping a stack are trivial, but by the time error detection and recovery are added, they are long enough that it is better to put each in a separate function than to repeat the code throughout the whole program. And there should be a separate function for fetching the next input operator or operand. The main design decision that has not yet been discussed is where the stack is, that is, which routines access it directly. On possibility is to keep it in main and pass the stack and the current stack position to the routines that push and pop it. But main doesn't need to know about the variables that control the stack. It only does push and pop operations. So we have decided to store the stack and its associated information in external variables accessible to the push and pop functions, but not to main. Translating this outline into code is easy enough. If for now we think of the program as existing in one source file, it will look like this. Hashtag includes hashtag defines function declarations for main. Main, external variables for push and pop void push double F, double pop void, and getop char s, routines called by getop. Later we will discuss how this might be split into 2 or more source files. The function is a loop containing a big on the type of operator or operand. This is main switch, a more typical use of switch than the one shown in section 3.4. Hashtag includes diode, H, hashtag include stlib, H /* for tof, / hashtag define maxop 100 / max size of operand or operator / hashtag define number 0 / signal that a number was found */ in getop char void push double pop void / reverse Polish calculator * main int type double op2 char s maxop while type equals getops equals eof a switch type a case number. Push atovs, break, case plus, push pop, plus pop, break, case asterisk, push pop, asterisk pop. Break, case dash, op2 equals pop, push pop, op2, break, case / op2 equals pop, if op2 equals 0.0, push pop, / op2, else printf, error, 0 divisor \n, break. Case, \n, printf, \t%.8g \n, pop, break, default, printf, error, unknown command %s \n, s, break, return 0. Because plus and asterisk are commutative operators, the order in which the popped operands are combined is irrelevant, but for and / the left and right operand must be distinguished. In push, pop, pop, / wrong * the order in which the two calls of pop are evaluated is not defined. To guarantee the right order, it is necessary to pop the first value into a temporary variable, as we did in main. Hashtag define maxval 100 * maximum depth of val stack */ int sp equals 0 / next free stack position / double val maxval / value stack / push f onto value stack * / void push double f. If sp maxval val sp++ equals f, else printf, error, stack full, can't push %g\n, f, / pop, pop and return top value from stack * double pop, void, if sp 0, return val, sp. Else printf, error, stack empty \n, return 0.0. A variable is external if it is defined outside of any function. Thus, the stack and stack index that must be shared by push and pop are defined outside these functions. But main itself does not refer to the stack or stack position. The representation can be hidden. Let us now turn to the implementation of getOp, the function that fetches the next operator or operand. The task is easy. Skip blinks and tabs. If the next character is not a digit or a hexadecimal point, return it. Otherwise, collect a string of digits, which might include a decimal point, and return number, the signal that a number has been collected. Hashtag include typed h. Int getch void ungech int / getop. Get next character or numeric operand * int getop. Char s, ANSI C, while s0 equals c equals getch equals c equals \t. s1 equals \0. If isdigit c and c equals return c / not a number / I equals 0. If isdigit c / collect integer part */. While isdigit s ++ I equals c equals getch. If c equals / collect fraction part */ while isdigit s ++ I equals c equals getch. S I equals \0. If c equals yof. Ungech c, return number. What are getch and ungech? It is often the case that a program cannot determine that it has read enough input until it has read too much. One instance is collecting characters that make up a number. Until the first non-digit is seen, the number is not complete. But then the program has read one character too far, a character that it is not prepared for. The problem would be solved if it were possible to unread the unwanted character. Then, every time the program reads one character too many, it could push it back on the input, so the rest of the code could behave as if it had never been read. Fortunately, it's easy to simulate getting to character by writing a pair of cooperating functions. Getch delivers the next input character to be considered. Ungech will return them before reading new input. How they work together is simple. Ungech puts the pushback characters into a shared buffer, a character array. Getch reads from the buffer if there is anything else, and calls getchar if the buffer is empty. There must also be an index variable that records the position of the current character in the buffer. Since the buffer and the index are shared by and must retain their values getch ungech between calls, they must be external to both routines. Thus, we can write getch, ungech, and their shared variables as #define buff size 100 char buff size. / buffer for ungech /int buff equals 0 / next free position in buff */ int getch void / get a possibly pushed back character * return buff 0 buff getchar void ungech int c / push character back on input * biff buff equals buff size printf ungech too many characters \n, else buff equals c. The standard library includes a function ungech that provides one character of pushback. We will discuss it in Chapter 7. We have used an array for the pushback, rather than a single character, to illustrate a more general approach. Exercise 4-3. Given the basic framework, it's straightforward to extend the calculator. Add the modulus, %, operator, and provisions for negative numbers. Exercise 4-4. Add the commands to print the top elements of the stack without popping, to duplicate it, and to swap the top two elements. Add a command to clear the stack. Exercise 4-5. Add access to library functions like ANSI, math, bin sin, exp, pow. Appendix B, Section 4. Exercise 4 to 6. Add commands for handling variables. It's easy to provide 26 variables with single-letter names. Add a variable for the most recently printed value. Exercise 4 to 7. Write a routine on Jetsas that will push back an entire string onto the input. Should know about and or should it just use ongets buff buff? Ongech? Exercise 4 to 8. Suppose that there will never be more than one character of pushback. Modify getch and ongech accordingly. Exercise 4 to 9. R and do not handle a pushback correctly. Decide getch ongech EOF what their properties ought to be if an EOF is pushed back, then implement your design. Exercise 4 to 10. An alternate organization uses getLine to read an entire input line. This makes and unnecessary. Revise the calculator to use this approach. Getch ongech 4.4 Scope Rules. The functions and external variables that make up a C program need not all be compiled at the same time. The source text of the program may be kept in several files, and previously compiled routines may be loaded from libraries. Among the questions of interest are Howard declarations compilation, written so that variables are properly declared during Howard declarations arranged so that all the pieces will be the program is loaded, properly connected when Howard declarations organized so there is. Exercise 4 to 5. Add access to library functions like ANSI, math, bin sin, exp, pow. Appendix B, Section 4. Exercise 4 to 6. Add commands for handling variables. It's easy to provide 26 variables with single-letter names. Add a variable for the most recently printed value. Exercise 4 to 7. Write a routine on Jetsas that will push back an entire string onto the input. Should know about and or should it just use ongets buff buff? Ongech? Exercise 4 to 8. Suppose that there will never be more than one character of pushback. Modify getch and ongech accordingly. Exercise 4 to 9. R and do not handle a pushback correctly. Decide getch ongech EOF what their properties ought to be if an EOF is pushed back, then implement your design. Exercise 4 to 10. An alternate organization uses getLine to read an entire input line. This makes and unnecessary. Revise the calculator to use this approach. Getch ongech 4.4 Scope Rules. The functions and external variables that make up a C program need not all be compiled at the same time. The source text of the program may be kept in several files, and previously compiled routines may be loaded from libraries. Among the questions of interest are Howard declarations compilation, written so that variables are properly declared during Howard declarations arranged so that all the pieces will be the program is loaded, properly connected when Howard declarations organized so there is only one copy. Howard external variables initialized. Let us discuss these topics by reorganizing the calculator program into several files. As a practical matter, the calculator is too small to be worth splitting, but it is a fine illustration of the issues that arise in larger programs. The scope of a name is the part of the program within which the name can be used. For an automatic variable declared at the beginning of a function, the scope is the function in which the name is declared. Local variables of the same name in different functions are unrelated. The same is true of the parameters of the function, which are in effect local variables. The scope of an external variable or a function lasts from the point at which it is declared to the end of the file being compiled. For example, if main, sp, val, push, and pop are defined in one file, in the order shown above, that is main. Int sp equals 0, double val, maxval, void push double f, double pop void. Then the variables sp and val may be used in and simply by naming them, no further push-pop declarations are needed. But these names are not visible in nor are and main push-pop themselves. On the other hand, if an external variable is to be referred to before it is defined, or if it is defined in a different source file from the one where it is being used, then an extern declaration is mandatory. It is important to distinguish between the declaration of an external variable and its definition. A declaration announces the properties of a variable, primarily its type. A definition also causes storage to be set aside. If the lines in SP, double val, maxval, appear outside of any function, they define the external variables SP and cause storage to val, be set aside, and also serve as the declarations for the rest of that source file. On the other hand, the lines extern int SP, extern double val, declare for the rest of the source file that SP is an and that is array, whose int val double size is determined elsewhere, but they do not create the variables or reserve storage for them. There must be only one definition of an external variable among all the files that make up the source program. Other files may contain extern declarations to access it. There may also be extern declarations in the file containing the definition. Array sizes must be specified with a definition, but are optional with an extern declaration. Initialization of an external variable goes only with the definition. Although it is not a likely organization for this program, the functions and could be push-pop defined in one file, and the variables val and SP defined and initialized in another. Then these definitions and declarations would be necessary to tie them together. In file 1, extern in SP, extern double val, void push double f, double pop void. In file 2,
int szkoły podstawowej równa się 0.
Double val, maxval. Because the extern declarations in file 1 lie ahead of and outside the function definitions, they apply to all functions. One set of declarations suffices for all of file 1. This same organization would also be needed if the definition of SP and val followed their use in one file. 4.5 Header files. Let us now consider dividing the calculator program into several source files, as it might be is each of the components were substantially bigger. The main function would go in one file, which we will call, and their variables go into a second file, main.c, push, pop, stack.c, goes into a third finally and go into a fourth file, getop.c. Getch, ungetch, getch.c. We separate them from the others because they would come from a separately compiled library in a realistic program. There is one more thing to worry about, the definitions and declarations shared among files. As much as possible, we want to centralize this so that there is only one copy to get and keep right as the program evolves. Accordingly, we will place this common material in a header file, calc.h, which will be included as necessary. The hashtag include line is described in section.
The hashtag include line is described in section 4.11. The resulting
The hashtag include line is described in section 4.11. The resulting program then looks like this. There is a trade-off between the desire that each file have access only to the information it needs for its job and the practical reality that it is harder to maintain more header files. Up to some moderate program size, it is probably best to have one header file that contains everything that is to be shared between any two parts of the program. That is the decision we made here. For a much larger program, more organization and more headers would be needed. 4.6 Static variables. The variables SP and in and are for the private use of val stack, C, buff getch, C, the functions in their respective source files, and are not meant to be accessed by anything else. The static declaration, applied to an external variable or function, limits the scope of that object to the rest of the source file being compiled. External static thus provides a way to hide names like buff and buff in the getch-ungetch combination, which must be external so they can be shared, yet which should not be visible to users of getch and ungetch. Static storage is specified by prefixing the normal declaration with the word static. If the two routines and the two variables are compiled in one file, as in static char buff size, / buffer for ungetch / static and buff equals 0, / next free position and buff * and getch void ungetch int c. Then no other routine will be able to access, and those names will not conflict buff with the same names in other files of the same program. In the same way, The variables that push and pop use for stack manipulation can be hidden by declaring sp and val to be static. The external static declaration is most often used for variables, but it can be applied to functions as well. Normally, function names are global, visible to any part of the entire program. If a function is declared static, however, its name is invisible outside of the file in which it is declared. The declaration can also be applied to internal variables. Internal variables are static local to a particular function, just as automatic variables are, but unlike automatics. They remain in existence rather than coming and going each time the function is activated. This means that internal static variables provide private, permanent storage within a single function. Exercise 4-11. Modify so that it doesn't need to use hint. Use an internal getOpungh. Static variable. 4.7 Register variables. A register declaration advises the compiler that the variable in question will be heavily used. The idea is that register variables are to be placed in machine registers, which may result in smaller and faster programs. But compilers are free to ignore the advice. The register declaration looks like register and x, register char c, and so on. The register declaration can only be applied to automatic variables and to the formal parameters of a function. In this later case, it looks like f, register and signed m, register long n, a register and I. In practice, there are restrictions on register variables, reflecting the realities of underlying hardware. Only a few variables in each function may be kept in registers, and only certain types are allowed. Excess register declarations are harmless, however, since the word register is ignored for excess or disallowed declarations. And it is not possible to take the address of a register variable, a topic covered in Chapter 5, regardless of whether the variable is actually placed in a register. The specific restrictions on number and types of register variables vary from machine to machine. 4.8 Block structure. C is not a block structure language in the sense of Pascal or similar languages, because functions may not be defined within other functions. On the other hand, variables can be defined in a block-structured fashion within a function. Declarations of variables, including initializations, may follow the left brace that introduces any compound statement, not just the one that begins a function. Variables declared in this way hide any identically named variables in outer blocks and remain in existence until the matching right brace. For example, in if n greater than 0, int I / declare a new I */. For I equals 0, I less than n, I++. The scope of the variable I is the true branch of the if. This I is unrelated to any I outside the block. An automatic variable declared and initialized in a block is initialized each time the block is entered. Automatic variables, including formal parameters, also hide external variables and functions of the same name. Given the declarations index, int y, f, x, y, then within the function f, occurrences of x refer to the parameter, which is an outside double, f, they refer to the external. The same is true of the variable y, int. As a matter of style, it's best to avoid variable names that conceal names in an outer scope. The potential for confusion and error is too great. 4.9 Initialization. Initialization has been mentioned in passing many times so far, but always peripherally to some other topic. This section summarizes some of the rules, now that we have discussed the various storage classes. In the absence of explicit initialization, external and static variables are guaranteed to be initialized to 0. Automatic and register variables have undefined, i.e., garbage, initial values. Scalar variables may be initialized when they are defined by following the name with an equals sign and an expression. In x equals 1, char squota equals \, long day equals 1000 L times 60 L times 60 L times 24 L, / milliseconds / day */. For external and static variables, the initializer must be a constant expression. The initialization is done once, conceptually before the program begins execution. For automatic and register variables, The initializer is not restricted to being a constant. It may be any expression involving previously defined values, even function calls. For example, the initialization of the binary search program in section 3.3 could be written as int search, int x, int v, int n are int low equals 0, int high equals n1. Int mid. Instead of int low, high mid, low equals 0. High equals n1. In effect, initialization of automatic variables are just shorthand for assignment statements. Which form to prefer is largely a matter of taste. We have generally used explicit assignments because initializers and declarations are harder to see and further away from the point of use. An array may be initialized by following its declaration with a list of initializers enclosed in braces and separated by commas. For example, to initialize an array days with the number of days in each month. Int days equals 31, 28, 31, 30, 31, 30, 31, 31, 30, 31, 30, 31. When the size of the array is omitted, the compiler will compute the length by counting the initializers, of which there are 12 in this case. If there are fewer initializers for an array than the specified size, the others will be 0 for external, static, and automatic variables. It is an error to have too many initializers. There is no way to specify repetition of an initializer, nor to initialize an element in the middle of an array without supplying all the preceding values as well. Character arrays are a special case of initialization. A string may be used instead of the braces and commas notation. Char pattern equals old is a shorthand for the longer but equivalent. Char pattern equals O, U, L, D, \0. In this case, the array size is 5 for characters plus the terminating \0. 4.10 recursion. C functions may be used recursively. That is, a function may call itself either directly or indirectly. Consider printing a number as a character string. As we mentioned before, the digits are generated in the wrong order. Low-order digits are available before high-order digits, but they have to be printed the other way around. There are two solutions to this problem. On is to store the digits in an array as they are generated, then print them in the reverse order, as we did with IDOA in section 3.6. The alternative is a recursive solution, in which print first calls itself to cope with any leading digits, then prints the trailing digit. Again, this version can fail on the largest negative number. Hashtag includes diode h/*print, print n in decimal * void print, in n if n less than 0, put char dash n equals n, if n/10 print n/10. Put char n% 10 plus 0. When a function calls itself recursively, each invocation gets a fresh set of all the automatic variables, independent of the previous set. This in print 123. The first print receives the argument n equals 123. It passes 12 to a second print, which in turn passes 1 to a third. The third level print prints 1, then returns to the second level. That print prints 2, then returns to the first level. That 1 prints 3 and terminates. Another good example of recursion is quicksort, a sorting algorithm developed by Karl Hoare in 1962. Given an array, one element is chosen and the others partitioned in two subsets. Those less than the partition element, and those greater than or equal to it. The same process is then applied recursively to the two subsets. When a subset has fewer than 2 elements, it doesn't need any sorting. This stops the recursion. Our version of quicksort is not the fastest possible, but it's one of the simplest. We use the middle element of each subarray for partitioning. /*sort, sort v left, v right, into increasing order * void sort, int v, int left, int right, int I last, void swap, int v, int I, int j. If left equals right, / do nothing if array contains */. Return / fewer than 2 elements /swap v left plus right /2. slash move partition elem slash last equals left, slash to v0 slash 4, I equals left plus 1, I equals right, I plus plus, slash partition asterisk, slash if v I v left. Swap v plus plus last I, swap v left last, forward slash asterisk restore partition elem asterisk slash xort v left last 1, xort v last plus 1 right. We moved the swapping operation into a separate function swap because it occurs 3 times in xort. Slash asterisk swap, interchange v I and v j asterisk slash void swap, int v, int I, int j, int temp. Temp equals v I equals vj equals temp. The standard library includes a version of xort that can sort objects of any type. Recursion may provide no saving in storage, since somewhere a stack of the values being processed must be maintained. Nor will it be faster. But recursive code is more compact and often much easier to write and understand than the non-recursive equivalent. Recursion is especially convenient for recursively defined data structures like trees. We will see a nice example in section 6.6. Exercise 4-12. Adapt the ideas of to write a recursive version of that is, convert print itoa, an integer into a string by calling a recursive routine. Exercise 4-13. Write a recursive version of the function reverses, which reverses the string south in place. 4.11 The C Preprocessor. C provides certain language facilities by means of a preprocessor, which is conceptually a separate first step in compilation. The 2 most frequently used features are #include, to include the contents of a file during compilation, and #define, to replace a token by an arbitrary sequence of characters. Other features described in this section include conditional compilation and macros with arguments. 4.11.1 File inclusion. File inclusion makes it easy to handle collections of #defines and declarations, among other things. Any source line of the form #include filename or #include filename is replaced by the contents of the filename. If the filename is quoted, searching for the file typically begins where the source program was found. If it is not found there, or if the name is enclosed in and do, searching follows an implementation-defined rule to find the file. An included file may itself contain #include lines. There are often several #include lines at the beginning of a source file to include common #define statements and extern declarations, or to access the function prototype declarations for library functions from headers like stio h. Strictly speaking, these need not be files. The details of how headers are accessed are implementation dependent. #include is the preferred way to tie the declarations together for a large program. It guarantees that all the source files will be supplied with the same definitions and variable declarations, and thus eliminates a particularly nasty kind of bug. Naturally, when an included file is changed, all files that depend on it must be recompiled. 4.11.2 Macro substitution. A definition has the form #define name replacement text. It calls for a macro substitution of the simplest kind. Subsequent occurrences of the token name will be replaced by the replacement text. The name in a #define has the same form as a variable name. The replacement text is arbitrary. Normally, the replacement text is the rest of the line, but a long definition may be continued onto several lines by placing a backslash at the end of each line to be continued. The scope of a name defined with #define is from its point of definition to the end of the source file being compiled. A definition may use previous definitions. Substitutions are made only for tokens and do not take place within quoted strings. For example, if yes is a defined name, there would be no substitution in printf, yes, or in yesman. Any name may be defined with any replacement text. For example, #define forever for winkyface / infinite loop / defines a new word, forever, for an infinite loop. It is also possible to define macros with arguments, so the replacement text can be different for different calls of the macro. As an example, define a macro called max. Hashtag define max, A, B, A, B, A, B. Although it looks like a function call, a use of max expands into inline code. Each occurrence of a formal parameter, here A or B, will be replaced by the corresponding actual argument. Thus the line x equals max, p plus q, r plus s, will be replaced by the line x equals p plus q, r plus s, p plus q, r plus s. So long as the arguments are treated consistently, this macro will serve for any data type. There is no need for different kinds of max for different data types, as there would be with functions. If you examine the expansion of max, you will notice some pitfalls. The expressions are evaluated twice. This is bad if they involve side effects like increment operators or input and output. For instance, max I++, j++, / wrong * will increment the larger twice. Some care also has to be taken with parentheses to make sure the order of evaluation is preserved. Consider what happens when the macro hashtag define square x x * wrong * is invoked as square z plus 1. Nonetheless, macros are valuable. One practical example comes from stio.h, in which and are often defined as macros to avoid the runtime overhead of a getChar-putChar function call per character processed. The functions in typed h are also usually implemented as macros. Names may be undefined with hashtag undef, usually to ensure that a routine is really a function, not a macro. Hashtag undef getChar. In getChar void, formal parameters are not replaced within quoted strings. If, however, a parameter name is preceded by a hashtag in the replacement text, the combination will be expanded into a quoted string with the parameter replaced by the actual argument. This can be combined with string concatenation to make, for example, a debugging print macro, hashtag defined print, expr printf, hashtag expr equals %g\n, expr, when this is invoked, as in print, x/y. The macro is expanded into printf, x/y, equals and g\n, x/y, and the strings are concatenated, so the effect is printf, x/y equals and g\n, x/y. Within the actual argument, each is replaced by backslash and each backslash by backslash, so the result is a legal string constant. The preprocessor operator hashtag provides a way to concatenate actual arguments during macro expansion. If a parameter in the replacement text is adjacent to a hashtag, the parameter is replaced by the actual argument. The hashtag and surrounding white space are removed, and the result is rescanned. For example, the macro paste concatenates its two arguments, hashtag define paste, front hashtag back, so paste, name, 1, creates the token name 1. The rules for nested uses of hashtag are arcane. Further details may be found in Appendix A. Exercise 4-14. Define a macro swap, t, x, y, that interchanges two arguments of type t. Block structure will help. 4.11.3 Conditional inclusion. It is possible to control preprocessing itself with conditional statements that are evaluated during preprocessing. This provides a way to include code selectively, depending on the value of conditions evaluated during compilation. The line evaluates a constant integer expression which may not include casts or hashtag if size of constants. If the expression is non-zero, subsequent lines until an or enum hashtag and if hashtag elif are included. The preprocessor statement is like the expression hashtag else hashtag elif elsif. Ina is 1 if the name has been defined, and 0 otherwise. Hashtag if. For example, to make sure that the contents of a file HDR, H are included only once, the contents of the file are surrounded with a conditional like this. Hashtag if, defined, HDR, hashtag define HDR. / contents of HDR, H go here */. Hashtag and if the first inclusion of defines the name's subsequent inclusions will find the name HDR, HHDR, defined and skip down to the hashtag and if. A similar style can be used to avoid including files multiple times. If this style is used consistently, then each header can itself include any other headers on which it depends, without the user of the header having to deal with the interdependence. This sequence tests the name system to decide which version of a header to include. Hashtag if system equals SYSV hashtag define HDR SYSV H. Hashtag L if system equals BSD hashtag define HDR BSD H. Hashtag L if system equals MSDOS hashtag define HDR MS-DOS H. Hashtag else hashtag define HDR default H. Hashtag and if hashtag include HDR. The and lines are specialized forms that test whether a name is defined. The hashtag if def hashtag if and def first example of hashtag if above could have been written hashtag if and def HDR hashtag define HDR / contents of HDR H go here * hashtag and if. Chapter 5. Pointers and arrays. A pointer is a variable